from particulate aerosols mixing with clouds, or from their reflective effect directly in scattering sunlight. And what you can see here is the white lines representing uncertainty show that the greatest uncertainty is in the reflective effect created when particles mix with clouds. But an important takeaway from this is that all pollution is thought to be producing this reflective effect around the atmosphere. This was highlighted in the reduction of those shipping emissions with new regulations in the International Maritime Organization in the past couple of years. And so there's a big question as to, as we clean up pollution, how much additional warming we might get. And so one way to think about these atmospheric climate interventions is as a replacement for the cooling effect of emissions. And the really important thing to emphasize, especially as pertains to the IREF community here, is what we don't know and what we need to research about these effects. So one of the approaches of climate intervention is associated with that cloud effect. The other one is associated with the effect that's been observed when very large volcanoes erupt. When Mount Pinatubo erupted in 1991, it emitted large amounts of aerosols all the way up into the stratosphere. And these aerosols cooled the planet measurably for a couple of years. And you can see in the chart a sort of the trajectory of cooling as aerosols took effect and then gradually dispersed out of the atmosphere. That was also associated with a recovery of Arctic sea ice. And so the takeaway from this is that there are observations which suggest that putting aerosols into the atmosphere can create cooling effects globally, regionally, maybe locally. And there are a lot of uncertainties and unknowns as to whether the benefits of those effects can be achieved in a way that outweighs their risks. So the three approaches that scientists have been looking at and have suggested for research involve putting aerosols in the stratosphere, in the lower atmosphere in the marine cloud layer, and as a less well understood technique, possibly putting aerosols in the cirrus cloud layer to thin clouds and release ultraviolet radiation. So these are the approaches. You'll hear a little bit about some of them today. And a couple of important facets, I think, for this community to think about is as climate impacts and precipitation effects grow, interest in these kinds of larger, more regional, more circulation-related kinds of interventions grow. They're growing around the world. So there's different kinds of research on these sort of approaches that are starting to emerge in all continents. There are some large-ish programs in the United States and the UK. And just in the past couple of years, international bodies, including 3 or 4 reports from the UN, and in the United States, an interagency report, as well as specific research work by DOE and NOAA, all recommending research on these climate interventions, both from the point of view of their potential to improve impacts, especially related to precipitation, and also for understanding their risks and what we might need to know from a safety and security perspective about them. And so from the point of view of this session and IREF, and what most people around the world are interested in, is could aerosols influence local, regional, or global climate to increase rainfall here in this region or in the region of interest? And it turns out that's a little bit of a hard science problem. You're going to hear about some of the science today, but in order to do that problem, what we want to be able to do is do projections of the region that include the future climate and weather systems, and that also include the ability to represent different scenarios for bringing aerosols or other kinds of limited area interventions into the system and what they would do. And right now, there are a lot of weaknesses in our ability to do that. And that includes the representation of some of the really fundamental processes in the models. It includes weaknesses in observations of the background conditions, especially aerosols in the low atmosphere. And it includes, of course, weaknesses or very early stages of research on specific interventions and what they look like and what their processes would look like in a model. So we in Silver Lining have worked with senior scientists, including scientists and government agencies in the US and the UK, to outline a roadmap for research, which is available on our website if you're interested. But I'm really pleased and honored today to introduce 3 senior scientists who are going to talk to you about elements of that research, a little bit of state of the art of where we are today and what's exciting in some of the facets and considerations of these interventions. So it's my honor here to be able to introduce you to the panelists, Jean-Francois Lamarck, who is the chief climate scientist at my organization, Silver Lining, and was previously at the National Center for Atmospheric Research. Oliver Branch, who is the co-coordinator of the Land Atmosphere Feedback Observatory at the Institute for Physics and Meteorology at the University of Hohenheim, Germany. Sorry about that. And Chris Leonard, a colleague, terrific scientist, environmental scientist at the University of Cape Town in South Africa. So please join me in welcoming these senior scientists for a really enlightening conversation. Thank you.
Good morning, everyone, and thank you for being here. So, I'm gonna have my presentation. All right. So, I'm gonna be covering kind of from a fairly high level, a set of recent developments in both modeling and deployment or outdoor experiments related to the topic of regional limited area climate intervention. So general overview, I'm going to be looking at some recent observations, recent relevant modeling, some recent field experiments, and then kind of go over next steps. So in terms of the general overview, just bringing it back into why we're here, right? So the goals that we're trying to achieve is to try to increase precipitation, rain enhancement, over a region of interest, and let's just assume for now that we're going to be talking about the Arabian Peninsula. So a lot of the discussions so far have been on trying to do that in what probably I would call it a direct way to affect precipitation rate, so cloud seeding, everything that has been discussing in the previous 2 days. So here I want to start thinking a little bit more differently about what can be done to affect precipitation, not so much by changing the clouds as they are, but much more changing the circulation in such a way that that would lead to increased precipitation. One way this can be done, and it's going to be the topic of the presentation by Oliver after me, is to try to use changes to surface albedo to really try to find ways to increase probably convective updrafts, just generation of convection, and then hopefully the associated precipitation or enhance existing convection through the added surface fluxes coming up of some perturbation to the local albedo. And so Oliver is going to be discussing that, so I won't go into detail. One thing that has been discussed over several decades, but it's starting to become a lot more general topic, is the topic of using clouds over the marine environment to try to use that as a way to increase reflection of the sun, and so the shore wave, forcing by increasing either the amount of clouds or their brightness. So this is the marine cloud brightening type of approach, which tends to use, let's see if this, no, it doesn't work, which tends to focus on using sea salt release as a way to change the characteristics of the clouds. Now we'll go into more details because I think there is a lot more to it than just this description, which is really about changing the clouds. And changing the clouds is huge. Right? If you change the amount of clouds globally by 1%, that's sufficient to reduce the climate warming as we have it, the climate imbalance. The heat imbalance at the top of the atmosphere is like a watt per meter square. Changing the albedo by 1% is 3 watts per meter square. So there's a lot of leverage in the clouds. As Kelly mentioned, there are another set of ways one can think of is to change the global circulation in such a way that it will have impact. So this is much more like harder to focus on what would be the impact, or designing an approach that would be specific to, say, the Arabian Peninsula, but as part of the outcome of doing something like stratospheric aerosol injections, then what would be the impact on the Arabian Peninsula versus what would be the impact on climate change? And I'll get back to this a little bit, but also the one thing that I'd like to make sure is that when we start talking about stratospheric aerosol injections, it's the details really matter. It's really, really tricky to come up with a general conclusion saying stratospheric aerosol injection is banned because it will have this impact. The point of those figures here is to show, like, the bottom two are just two ways of doing injections. And so but the answers are very, very, very different. And so one have to be really careful about making statements of what people call geoengineering, stratospheric aerosol injection, because the details really matter. One thing that we have been able to observe over the last few years as related to changes over the ocean is the reduction in sulfur emissions from ships. So in 2020, there was an International Maritime Organization effort to reduce the amount of sulfur that was emitted by ships by putting scrubbers over ships. And so that has led, and that's what that figure there with the dash is. So there was a decrease in emissions anyway globally in terms of SO2 emissions, but then there was a drastic reduction from that. And so now the beauty of it is that we have enough satellite observations and that we can actually try to start identifying the signature of this reduction. And so this is what this figure on the bottom left is trying to see for a variety of conditions, and I'm happy to go into those details during the question session. But the bottom line is that we can actually see from satellite measurements the track of changes here in the effective radius of the aerosols associated with the emission of ships, right? So by comparing the time when you had strong sulfur versus the time you don't have strong sulfur over the last few years, you can actually really see on a track-by-track basis, very similar to what Kelly was showing, those tracks of the coast of the US. This is a representation, except that now we have it globally. It happened everywhere. All ships had to do that. The way this translates into climate is first in what we call radiative forcing. So radiative forcing is basically a measure of the change of the radiation that reaches the surface associated with a special impact. And so there are two ways radiation interacts with aerosols. One is what we call the direct, so it's really changing the amount of radiation by the fact that there is a layer of aerosols, like we see on very polluted days. Visibility is very different, so this has an impact on the radiation, and it's the top panel, the direct. The indirect is the interaction of aerosols with clouds, thereby changing the cloud structures or the cloud reflectivity. And so that has, in and of itself, an impact. And it's actually, the scales are different between the two figures, so it is pretty clear that over the region, say in this case the Atlantic Ocean, the interaction between clouds and aerosols is the dominating effect. However, if you start looking at areas like the Arabian Peninsula, it's a very, very different story. There are not enough clouds present over the ocean to really enable a strong cloud aerosol interaction. Instead, you end up with a forcing that's much more associated with having more aerosols. So this is what we end up calling marine sky brightening versus marine cloud brightening, to really reference the fact that it's the amount of radiation that's reaching the surface that is changing, not the changes in clouds. And so to me, this is where understanding the whole system and understanding the way those shipping emissions have been affecting radiation and cloud and aerosol distribution is really key in telling us what kind of effect. If we were to try to reproduce something like that by putting sea salt aerosols, not sulfate, we're not going to start polluting. But if you were to try to do this with sea salt, what would be the likely impact based on this analysis? In terms of modeling, with collaborators, we've been really trying to understand what is the potential for marine cloud brightening. And at this point, this is still very exploratory. We're still really trying to understand the basis of how it functions. We're using climate models which have limits, as Bjorn was discussing, in particular the way we represent aerosols and how they interact with the clouds is very dependent on the model. So there is a lot of uncertainty. And so we're trying to go through the exercise of working with different models, with different groups around the world who do have the capabilities of doing this. And as part of this analysis, we're working with people, in this case, from Exeter in the UK. And because we're really at the level of trying to understand how it works, we're splitting the globe, or the oceans, into a bunch of areas over which we can do a perturbation in terms of sea salt, increasing the amount of sea salt emissions. Sea salt emissions are part of the climate. All climate models have to include sea salt emissions because it's part of the natural cycle. We have to have that to understand what are the background conditions before we do any scenario simulations. So this is just a way of using what we're doing and then taking it to the next level by doing perturbations. So if, in this case, there is the Indian Ocean area, which the NI box here. And then what you see, so this is the change in precipitation associated with a change in sea salt emission over that box. And what we're seeing is that if you put 5 teragrams, 10 teragrams, or 50 teragrams, those changes become more and more significant, and the overall structure tends to be similar. And one thing that's really interesting in this aspect is that over the Arabian Peninsula, or some of the regions around it, we're actually seeing an increase in precipitation. So again, this is by changing the clouds and the aerosols over a certain area, you're able to change the circulation enough, the regional circulation enough, that it would lead to an increased precipitation. And the left panel is really showing, because the clear sky is the total forcing. IREF is the effective radiative forcing, is a measure of the total forcing, but for that region, it's solely driven, or almost solely driven, by changes in aerosols. So again, I think we have to think of marine cloud brightening as something broader, that it changes the overall structure of the atmosphere. In terms of relevant field experiments, I would probably put just a couple of them at this point. This one is, on the left, is from the Australian groups looking at the Great Barrier Reef, trying to use marine cloud brightening as a way to reduce temperature over the Great Barrier Reef. One thing, so they're putting experiments like putting propellers that release large amounts of sea salt into the atmosphere, and so that's what the ship is showing there. And what you see is exactly what I was trying to indicate earlier. You can see that even though this is just a plume of aerosols, you can see the reflection that's associated with it, right? So the idea is, can we actually make enough of that it would change the structure of the circulation? Silver Lining has a similar experiment that we've been trying to get over in California. Same general technology with the details on how much and what size of particles you want to have. The big question in my mind is that at this point, people have been able to do the left side, the middle, which is really trying to look at what happens in the first few meters, but there's really not a good understanding of what happens kilometers after that. So there is a need on understanding, and I think this is the interaction with this group is going to be very critical, because it is very similar in some of the aspects of rain enhancement, of understanding how do you get the big picture of precipitation enhancement from just a set of limited measurements. So what are the next steps, in my opinion? So based on what I've shown, I think there is enough to trigger interest. In my mind, it's enough to start asking the question, if we are to perturb sea salt emissions in the vicinity of the Arabian Peninsula, for example, what are the changes in circulation that we could expect to see from that? And so this is the sort of question that we're trying to address at the global scale, right, with those global models. But at some point, it's not going to be sufficient, because you want to really capture much more of the topography, much more of the details, this land, sea, breeze, and all that. So the details will really matter. So I think there is enough showing that there is potential, but we have to really dig into the details. At the same time, both climate is changing. There is the potential for large solar radiation modification scenarios, such as stratospheric aerosols or global marine cloud brightening. So I think it's important also to understand how the changing climate will impact this before we try to do, or at least in unison with what we're trying to do with some regional modeling. Understanding for that, we have to understand what are the conditions here. Maybe there's a way to do some small-scale experimentation to understand the aerosol evolution in this area and its radiative impact. So explaining, so in this figure, I'm trying to convey the fact that, so this is very similar again to the figure that Bjorn showed on the first day, but the climate change signal over this area is for an increase in precipitation, right? So we have to understand how is this going to be happening, what are the drivers, what is the likelihood of such changes, and then combine that with information on what could be done on the local or the regional level. And with that, I will end my talk. Thank you.
Okay, testing. Welcome everyone. So it's great to be back in Abu Dhabi since our project finished our first cycle project in 2018. So it's great to be back, and it's great to have this opportunity to come and speak here about the work which partially has been done as part of IREF, but also we started this research also before. So just an introduction, I'm a senior scientist at Hohenheim University, Institute of Physics, and I'm also now head of the Land Atmosphere Feedback Observatory. So I'm really a measurements guy, as well as modeling, so mesoscale modeling, and my passion is to try and combine these two things in order to answer questions about the atmosphere, especially land, how the land interacts with the atmosphere and so on. So let's make a start. So it's great that Jean-Francois put this work in context in a wider scale. I think regional geoengineering or climate engineering is definitely becoming a topic now. It's a hot area of research, and really like finding regional solutions to regional problems is narrowing it even possibly a little bit further. So we have things like continental or national afforestation schemes possibly as a way to change temperatures through evaporative cooling and changes in circulation. We also have marine cloud brightening or sky brightening, has been mentioned. Cirrus thinning is also a possibility to change the forcing, but this can also be done just at a regional level. It doesn't have to be done globally. Cloud seeding, I'm not quite sure where this fits into limited area, but it seems to me that it does form part of this because it can just be contained in a regional area. So we come on to our hypothesis now about heater islands. So our overarching hypothesis is that low albedo surfaces can enhance clouds and precipitation via surface heating and convergence. So, however, we're not only necessarily changing the albedo, we're also changing surface roughness as well. So this also can have an effect. So you can see here on the right, there is a patch of land. Here we have 10 kilometers scale, for instance. And we've given this kind of a pet name. We call it the Cloud and Precipitation Reactor. I quite like this because it's like CPR, breathing life back into the desert. So in theory, this could be made up of any dark substance. It could be black foil or coated panels, for instance. However, it doesn't have to be that. We've also done a couple of papers where we talk about using desert plants, xerophyte plants, for instance, like jojoba, which is a very hardy shrub which can survive in very dry environments. And if it also has a low albedo, especially as the background desert, the surrounding soils, this can have the same effect, although it does have a different roughness. So these all has to be taken into account. So this is basically the idea, is putting large patches into the desert in order to bring about changes in circulation and so forth, and the ultimate goal is to really produce clouds on a convective cell. So just a background about jojoba. So this comes from the southwest United States. That's where it's indigenous to. and it has a very valuable oil which can be used for cosmetics and so forth, so it's very valuable. And we've done a lot of research on this, so I did a one-year field campaign actually in the state of Israel, where they have very, very large jojoba plantations, and we measured radiation fluxes, everything, energy balances over there, to really see what interaction there is with the atmosphere, and if it would be useful for this kind of application. There are other plants too, like jatropha, which could be used, but jojoba is definitely an ideal candidate for this. So actually, we were part of a feasibility study which was run in Marwan's group, in Tamimi's group in Masdar, and where a feasibility study was done for the UAE for various kinds of crops, and jojoba was also included in there, taking into account all kinds of different factors, distances to pipelines, quality of soils, and so forth. And came out that jojoba has a pretty good potential in the UAE, at least from a kind of a basic study. So it's worth looking at for sure. Okay, a paper that just came out last year in ESD. So in that paper, we tried to answer three research questions which we hadn't really covered before. Really, what scales are needed for these patches of land in order to produce the effect that we're looking for, production of a convective cell or cloud? And really, we want to look at the lower end of the scale. Previous studies, we'd looked at kind of 100-kilometer size patches because we really just wanted to see, okay, let's make a giant one and see what happens. Now we want to sort of get real, and we trying to explore the lower ends of this scale. And so we did that in this simulation study. Also, what level of enhancement can be expected? So based on the size that you have. And also, what are the main physical processes? Explore those a little in more detail. Particularly also the interaction with the sea breeze, which happens almost daily in the UAE. One can expect that to have an effect because it's penetrating far inland, 50 kilometers or so, quite easily. So all these questions we wanted to cover. So just a little background on the physical principle of this rainfall enhancement. As some of you may know this already, you've seen us, but for those who haven't, I'll just go through. So we have basically a darkening of the land surface. Here's just an example close to Abu Dhabi. And this, as I said, could be a number of surfaces. It could even include solar PV surfaces as well, which we'll explore later. So the darkening of the land surface has a couple of effects. So in general, you have a higher solar radiation absorption. You have a lower albedo. Also, you have plants which are very water use efficient. They can actually close their stomata during the day, and you get a very strong sensible heating from there. So if you put those together, whichever surface you're using, you get a lower heating of the lower atmosphere. So this has an effect on a large enough scale that you get start to get a low pressure system directly over the area itself. You also get changes in surface friction as well, which can also add to this effect. So what we're seeing is that you basically get a formation of convergence lines, particularly at the back, at the lee side of the patches. And you can see just an example here where the arrows are coming together, and you can also see the heating effect on the ground as well. If the atmospheric conditions are conducive, and this depends a lot on the stability, the temperature profile in the atmosphere, how stable it is, and how much convection inhibition there is. If conditions are right, then we can get cloud formation and even a convective cell. And this is where we get our rainfall enhancement. So it's just a simple schematic of how this whole thing works. So, but a video can tell a story of 1,000 words, so I think it's quite nice to just show you how this works, actually. So here we have a simulation that we did on the coast of Oman, close to Mazira Island. And here you can see the red outline of a patch. And we've got two vertical profile panels here that you can see humidity on the left and temperature on the right, potential temperature. We've also got 10-meter wind flow on the bottom, and we've also got on the fill contours is sensible heating at the ground. So we can actually animate this now, and we can see at the start of the day, you can see already this pink area. This is where the ground is heating up, so you get a differential heating, and you get a heat low pressure, something of about 1 hectopascal negative compared to the surroundings. We start to get wind convergence at the back, of the plantation, or the CPR, and we start to get a mixing, destratification of the temperature profile, and basically, a vertical mixing of moisture and heat. Once it gets up to the level of free convection, we have free buoyancy, and we have this convective cell basically developing. And we also get strong updrafts and downdrafts. So this is just what is happening in the model. Quite a simple process. Okay, so in the later simulations, so we trying to look at the lower scale limits. So here we use the Wharf-Noah MP model. If anyone wants to discuss what physics we used and everything, we can talk about that. So essentially this was just over 2.5 kilometer resolution, so a convective permitting scale. We used ECMWF analysis to drive it, so very high quality forcing data at 9 kilometers. And we used a large domain. So the main domain we're looking at is this dotted line around the UAE. And then within that simulation, so we did a control simulation, and then we also simulated different sizes of these CPRs, so in 2 different places, and from 10 kilometers and then going up in scales of 10 up to 50 kilometers. So, and we really want to see if the 10 kilometer has an effect or not, and how the impacts scale with the size of the area. By the way, this model chain was also we did a 1-year model evaluation. It was a very expensive model run, and we compared it with 50 weather stations in the UAE, so for temperature, humidity, winds, and the model performed pretty well. The winds were a bit too high, but everything else was working pretty well. So we're quite comfortable that this model chain at least does quite a good job in terms of the circulations and so forth. Okay, so in order to simulate the CPRs, what we did is we just changed the land surface data inside the model, so the parameter tables. So, for instance, we here prescribed just the top of the canopy, so a low, flat surface, pretty much like a solar panel or something like that, but it's kind of a generic flat panel. We also changed the background albedo. So typically in the desert, you can have up to 35% reflection. So here we're changing it down to about 5%, something of that order. And this is just put into the model in order to get change those land surface characteristics. So we did 4 cases and of a 24-hour period, and these cases were selected for a kind of moderate instability. We want to see some reaction, and it's nice if you have some conditional instability there. So we chose those just based on some profiles. And then, just to give you an example, so here on the left you can see the control run. So even though you have these squares, it's just dotted lines, there's nothing actually there. This is just with no change in the land surface at all. And you can see there is a little bit of rainfall. This is rainfall that hits the ground. If we look at the 50-kilometer plantations, you can see that there is an increase directly over the plantation. Yeah? It's quite obvious that it's there, also with the other one as well. But it does also change the distribution a little bit of the rainfall as well. But if we just focus in on those areas, you can really see that the 50-kilometer does have an effect. If we want to look at quantities, here we just summed up the total mass of the water in these 2 circular areas. And then you can see at the top, there is a big difference here. I would like to point out straight away that these amounts are illustrative. I wouldn't expect the microphysics to perfectly produce how much water there would be. I think more work definitely needs doing on that. I think what's important to look at is that the quantities really change here. I'm happy if one produces a convective cell by itself than not, before looking at the actual quantities of rainfall itself. Nevertheless, I think it's illustrative to show that we do have an increase, but more work needs to be done to see if those amounts are representative, let's say. So here we have these total water volumes over all the cases, and on the right you have the control run. And we can see there does seem to be like a lower threshold here where you're getting effects. So 10-kilometer patch doesn't seem to have a huge effect when you compare it to the control simulation, but as soon as you go over that, 15 to 20 kilometers, we're starting to get effect, and it really scales with the area. So it's slight curve as well, as you would expect, because the area is the square of the side. So you can see that there's a clear scale enhancement here. Now 10 kilometers, when you're doing a 2.7 degree run, 2.7 kilometer, is getting to the lower end of what you can resolve. But we have done some LES runs at 100 meters, and we're getting basically the same results. This hasn't been published yet, but you're really getting around about 10 kilometers somewhere before you start to see an effect. So we're quite comfortable. And this also reflects the literature, where they're looking at sizes of soil moisture patches and how this affects circulations. And around about that 8 to 10 kilometers is quite feasible, actually. So if we could quantify how much water we're producing with the model, then you could also translate that into exactly what that water is worth. So here, you could also put this into the annual water supply for people based on water consumptions. However, as I mentioned, there is a great deal of uncertainty here, of course. It's very sensitive to the microphysics scheme that you use. If you use Morrison, Thompson aerosol aware, for instance. And so it's very dangerous to say, okay, this is how much water we're going to get. Also have many other things as well. You have the boundary layer, surface layer schemes, which are very sensitive. And the initial conditions. If I start the model 6 hours earlier, I'll probably get a totally different result. You still get rain, but the amounts and the distribution could change entirely. So it's very hard to extrapolate from one run. And so either you resort to doing taking statistics over a season or even many years, which would give you more evidential support, let's say. But to really look at quantities, I think we need to start going in the direction of data assimilation, quantitative precipitation estimation, and so forth, which is a huge effort, of course. But I just wanted to get that caveat in. Okay, so what was interesting is there's quite an interaction with the sea breeze, which I didn't necessarily expect. So there's often a daily sea breeze, and here we can see that on this particular case, on the 27th of June, there was a front coming in with the sea breeze, and it brought in a large area of high cape. Okay. Also, we used updated sea surface temperatures, so we're very careful to get the sea surface temperatures right in the model from Copernicus data. At the same time, this same front also brought in a low convective inhibition wave as well, and this passed over the plantation. But this isn't always the case. Very often when the cape goes up, the convection inhibition also goes up as well. So just on this particular time, these occurred together, and really you could see what happens, this interaction with the sea breeze. Again, I can show you a little bit of information. If you look on the left is the control, the right is the 50 kilometer, and we can see this convergence line, this is low-level convergence, coming over the CPR. We can look at it again. If you look on the right-hand side, you can see that this convergence line, when it happens, is really strongly amplified. So you're getting much stronger updrafts, this motion of air, and you can see this convective cell developing on the right. I think that's very interesting, especially as the UAE has this very strong sea breeze effect. So these regional aspects have to be taken into account as well, not only just that it's hot and you're lowering the albedo, really the local effects do matter. So going even further, what we would like to do is to be able to predict what are the conditions where this will work, and also where do these conditions occur. This is the intelligent solution part of the title, is really, we don't want to waste our time trying to do this in an area where it's not going to happen. So based on kind of a one seasonal run that we did in Oman, here we have some impact days, we can use this information to look at the background conditions under which they will occur. And we actually came up with this analysis here, where we're looking at different variables relating to the dynamics, so the wind shear. So we know that wind shear, the higher the wind shear is, this tends to rub out mesoscale circulations, or it makes them harder to form a coherent circulation. So this definitely has an effect. We have stability here, we're using the convection triggering potential, and also humidity as well. And we can see the blue days are the wet days, and the red days are where there was no impact occurring. And typically, as may be expected, where you have high humidity, you also have high instability and also low wind shear close to the surface. also correlates just to the wind speed as well. This is when you tend to get the effects happening. So it's a kind of first order look at the conditions where the wet, the impacts can happen. The same model run was done over the state of Israel, and in summer, nothing happened. We got no effects whatsoever. In other seasons, maybe this could happen, or in autumn or spring, for instance. But typically, you can see that the wind shear is too high over the state of Israel, and it also tends to be more stable. Very typically, at this time, what we noticed, as soon as you get above 800 hectopascal, suddenly the air gets very dry. There's no moisture there, at least at this time of year anyway. So it's interesting to compare those regions. Then, using those three variables, we came up with just a simple statistical threshold method in order to create an index. So just rating the levels of these conditions in order to come up with a number. So here we have just a snapshot of how the index looks in the UAE. So we can see certain areas at this time have a high index. This means it's more likely to produce an effect. Going a step further, we can make statistics of these. So for instance, here, during this one summer period, we found that there's anything up to 15 days where there's a high probability of enhancement. So this looks good for certain areas. The only weakness about this is it doesn't seem to work very well in the mountains, because we look at a low-level humidity index and the mountains are going over that. So we have to find a solution for this. The other possibility in the future is that we can also take a machine learning approach really to try and take into account the huge variable space in the models to try and get better information on making an index more accurate, and also to incorporate more processes that we are not looking at here. This can be applied on a global scale as well. Here we just look at this index based from IREF data, so climatology. And we can see that at different times of the year, different areas are getting, so obviously we are interested in arid regions here. So we have hot region is the Saudi Peninsula area, all this region. Also the southwestern United States, where we actually have a paper before which shows quite strong results. So the Sonoran Desert area, Baja California, and so on. We also have other regions, Namibia, and possibly a couple of other regions too. So, but I would say this is like a first order look. Obviously there are regional peculiarities to do with coastlines, orography, things like that, which have to be considered. But just from an overall stability and humidity point of view, it gives us a nice first order approach. Then we can say, okay, let's go and look at those areas. It looks like we have a good chance there. Okay, so a little bit about the implementation. So any CPR, a large area that you put into the desert, it would be optimal if we could have a modular and scalable system, which doesn't do much environmental impact to the surroundings. It should be robust to withstand the heat, easy installation and removal, and also preferably low environmental impact, no pollution, no damage to the soil, and so forth. So a possible idea is that such a project could be scaled. So you start off on a smaller scale and then you scale up. So for instance, we could start off with a 1 or 2 kilometer square and do measurements and research on that area as well. There are some limitations to doing that, but it's certainly, we can look at radiation fluxes and so forth. It's a bit harder to look at mesoscale circulations and other things because that just requires a larger size for these things to occur. Nevertheless, we can still get a lot of information. Then, so here's some things that we can measure. Then over time, we can scale the whole project up until you're getting towards the size when you really expect to get an effect, so 10 kilometers or whatever that happens to be. So what happens when we do get some rainfall? So a certain proportion, in the model at least, falls on top of the area, but a great deal of it also falls outside, especially to the lee side of these areas as well. There's a possibility to collect the water directly. May sound a bit far-fetched, but we did have an idea how to do this with some pipelines and sloping panels. Actually, our university liked it so much they gave us the money to get a patent for this, so it took 5 years. So we can talk about that too. Any water that falls outside, this could possibly go towards recharging the groundwater or using to grow plants also. There's also a possible synergy with cloud seeding. If you can create clouds that remain fairly static and predictable, you could possibly augment this method using cloud seeding as well, which offers a very nice synergy idea. We also have the possibility to use composite surfaces. Nobody says we have to only use one surface. We could make it up of dark panels, solar PV, and also plants like jojoba as well. And this could actually provide a lot of synergies to do this and make it more attractive. Okay, so our bold statement is that CPRs enhance convection initiation through heating and could provide a significant annual water supply extra. And optimal scales are likely to be more than 10 kilometers or something of that order, though more work needs to be done on that. So the effect does seem to increase with scale, as one might expect. And these impacts can be predicted and forecasting using such indices and so forth, and climatologies. But implementation will need multidisciplinary studies and regional expertise as well, especially to do with economics and everything like that. So I think with that, I will leave you there. Thank you very much.
Morning, everyone. While my presentation comes up, my name is Chris Leonard. I work at the University of Cape Town in South Africa. I was very surprised to get the email inviting me to this meeting. So I emailed back and said, "Are you sure it's me you want?" And I was assured it was. But to start off by thanking the organizers for inviting me, really grateful. I've learned a lot over these last 2 days and look forward to the rest of it. In particular, thanks to Hamda, who put up with all of my very naive questions about the meeting and what was expected of me. So thank you so much. I really appreciate the work and the invitation. Yes, I've been asked to talk about it's got the auto advance, so let's not do that just yet. I've been asked to talk about the impacts of solar geoengineering on rainfall enhancement programs, as we all have really, but with particular talking about the Clausius-Clapeyron relationship. So what does greenhouse gas warming and solar geoengineering mean for Clausius-Clapeyron? And I've just structured it in this way where I'll talk a little bit about climate change, what the impacts or implications for Clausius-Clapeyron might be, what Clausius-Clapeyron is, what SRM or solar radiation modification might do to that, the implications for rainfall enhancement, and then just end off with some questions because as you've heard from the two previous speakers, everything we do raises more questions, which I guess is research. So let's start with global warming. We know that as the Earth warms, the global rainfall will increase as things get warmer. This is a map from the IPCC Interactive Atlas, and it's showing for rainfall change as a percentage in the medium term, so 2041 to 2060 odd, under a high emission scenario, how rainfall changes. And you can see where there's green, it gets wetter, where there's brown, it gets drier. So where I live in Cape Town, there's brown, and that's a very robust brown. And this is from 33 different global models that we see. And we understand that this is correct because of the Clausius-Clapeyron relationship, and this is written with meteorology and for climate applications. And we know that the saturation vapor pressure of water in the atmosphere is a function of temperature. So much so that the dependence of the saturated vapor pressure on temperature changes approximately exponentially. So for every 1 degree Celsius change in temperature, the amount of water vapor in the atmosphere increases by up to 7%. And we are busy with the bulletin, the BAM's State of the Climate Report right now. And in that State of the Climate Report, we're going to write 2024 was the wettest year that we've seen in the records. And we're also going to write that also the most extreme rainfall has fallen in 2024 in the records that we have. So this Clapeyron relationship and the warming is playing out in real time. We are living climate change right now. We're living global warming. Zooming in a little bit to that rainfall change due to our emissions. This is the same map zoomed in, just a little bit different in that there's some diagonal lines there. And those diagonal lines are an indication of robustness of the signal change. So basically, if an area is underneath a diagonal line, it means that about 2/3 of the models do not agree that it's a solid signal. So it could be just because of natural variability, the change that you see there. So there's no statistical significance underneath those diagonal lines that you can see, and most of the Arabian Peninsula sits under that. So we are still a little bit unsure, the models at least are, that there's not a robust change signal to this. However, we plow on. We can zoom in to regions. So on the interactive atlas, you can zoom into a region, and this is representative of the Arabian Peninsula. And here I'm looking at total precipitation change by month on the y-axis and by year on the horizontal axis. So we're starting in 1980 odd and heading out to 2100. And if you look in the months August, September, October, towards after 1950 or so, you can see for the Arabian Peninsula that this is where the rainfall change, according to these models, occurs. So that, what would that be? Autumn, right here? So that autumn period is projected by many models to be getting wetter, particularly in September. That's the rainfall change. What about the temperature change? So here there are very few diagonal lines just below Greenland. Maybe Trump won't want it because there's diagonal lines there now. But the temperature signal is much, much stronger, much more robust than the rainfall signature, and it's warming everywhere. And this is now also temperature change in the medium term under SSP 245. So I've just changed the scenario to a more middle of the range scenario. And what you can do with the interactive atlas is don't just look at temperature, but look at some metrics of temperature. So what might be meaningful? And here I've pulled out again for the Arabian Peninsula, days with temperatures above 40 degrees, and this is the change signal that we can see there. Relative to 1986 to 2005 period under SSP 245, and this is from 27 models. And again, if you look from 2050, does this have a laser? Yes, it does. No, it doesn't. If you look from 2050 odd, maybe 2040 odd, how things get much, much warmer, much, much faster in terms of the number of days above 40 degrees. So much so that from 2050 on, these models are saying that there are 4 to 5 more days per month with temperatures above 40 degrees. And when you take that, if you look at September, you can see that it's very marked change, that goes up to between 6 and 7 days per month in September above 40 degrees. And when you accumulate that, it ends up in the whole summertime here, you have between 20 and 25 more days above 40 degrees in the summertime. And that might be a concern, I don't know, but you do need to then think about what are the impacts of these types of changes? What does it mean to have almost 2/3 of a month more of days above 40 degrees? And this is when we start thinking about the impacts and what can we do about these impacts. And solar radiation management or modification, as Kelly introduced earlier, is one of the ideas that have popped up here. So we've got a couple of scenarios painted out in front of us of what we could do. We could do nothing, just keep on emitting emissions as we go along, and that would be disastrous because that would be like an SSP 585, we're all going to die type of scenario. We could do mitigation, which we must do, but the thing about mitigation is that it is slow, and it also does not take carbon dioxide out of the atmosphere. So basically, emit, we stop emitting, we get to net zero, but there are still these vast concentrations of CO2 in the atmosphere. We are still warming, we're still experiencing climate change. So another option we can explore is called carbon dioxide removal, where we actively try to remove carbon dioxide from the atmosphere, and this can be through planting trees or mechanically, technologically, which is also a slow process because we've spent 100 years putting CO2 into the atmosphere. We're not going to be able to take it out of the atmosphere in the next 20 or 30 years. So that's slow, and the y-axis the x-axis on this curve is actually to about 2200. So it's a 200-year line. So we are committed to warming for a very long time as we go into the century. So then the question comes, in terms of the impacts, can we do something about it? And this is where solar radiation management, or SRM, steps in. And what SRM, as Kelly explained at the introduction, is trying to reduce the amount of rainfall by just 1 or 2, the amount of solar radiation getting into the Earth system by 1 or 2%, and that can result in some cooling effect. Really important to understand, this does nothing for greenhouse gas concentrations. Those concentrations are still there. You're still suffering all of the consequences of increased CO2 in the atmosphere and increased CO2 in the oceans. So this is very much an emergency break the glass in case of fire type of measure. And Kelly explained about what SRM was and what it does, as said Jean-Francois, so I won't go through that slide again, except to say that it increases the albedo of the global atmosphere, really. And the two that I'll mention are the volcanic eruptions, so injecting sulfates into the stratosphere to make like gajillions of tiny little mirrors to reflect incoming solar radiation, and marine cloud brightening that Jean-Francois spoke about. So what does SRM do to the Clausius-Clapeyron? It basically reduces your temperature because you're not allowing, you're stopping some energy coming in from the sun to come into the Earth system, so you are reducing the temperature that comes in. And that is really the simple part of what we're trying to do, or the idea behind it. We know that this works because we have natural analogs, again, as was mentioned earlier. So for SRM, for injecting stuff into the stratosphere, with each volcanic eruption, this is the curve on the left, it shows that globally temperatures decreased, the global temperature decreased after each of these volcanic eruptions. And then on the right, and again, Kelly mentioned this, is that through the legislation that reduced sulfur coming out of ship stacks, there's a net. It lowered the albedo of these clouds, and it also brightened the sky, so more energy from the sun could come in to the system, into the Earth system. And that actually has been computed to have a net radiative forcing of about positive 0.2 watts per square meter. So it is a warming effect. So you clean up the pollution, the Earth gets warmer. And we understand why that is because of this. So we know that this works for temperature, both in the stratosphere and also through marine cloud decks, marine cloud brightening, that this could work in the solar radiation modification context. What does it mean for rainfall? Globally, when Pinatubo erupted, the graph on the right-hand side, you can see that when Pinatubo erupted, the freshwater discharge and land precipitation both decreased for about a year after that eruption. So it did have a global effect on precipitation and water availability when that happened. So again, we take from this that if you do this, some type of solar radiation modification, it will have an impact on temperature, it will have an impact on global rainfall. And you can explore this a little bit. This is something that's just come online maybe 3 or 4 months ago from a group called reflective.org. And you can explore what different scenarios there might be. So what you're looking at there at that map is the world at under SSP 245, so middle of the line type of scenario. And that's what it would look like if there were some kind of solar radiation management to keep the world at 1.5 degrees above pre-industrial. That's what it would look like with just greenhouse gas emissions. And then on the right, there's a time series that's showing the world without SAI, and then that would be temperature, and that would be the world with SAI. So you're trying to maintain a temperature at 1.5 degrees above pre-industrial. You can do the same thing with rainfall, or water availability is the metric that they use. So that's just greenhouse gases, only greenhouse gas emissions. And that is greenhouse gas emissions and SAI, which is stratospheric aerosol injection. And you can see that when you do SAI, it's a bit drier. So greenhouse gases, if you look at the time series again, you warm the atmosphere, you get more water availability because the Earth, because of Clausius-Clapeyron. When you cool it, through SAI at least, then that drops off again and becomes a little bit more. One thing to be aware of on this website, they use just one model. So this is one model's result. We have to understand across a variety of different models. We can then, on this platform, zoom in to some region, and if we zoom in onto the Arabian Peninsula again, we can see that with warming, where temperatures, this goes up to 4 degrees by the end of the century, and if you were to do SI, that blue curve, it doesn't actually reach 1.5 degrees. So despite this intervention, you wouldn't get back to anything that resembles normal. You can do the same thing with rainfall, and here the signal is different, where for this region, for this model, again the caveat to the model, it's indicating a reduction of water availability over the region. That might be temperature related. And then if you do some type of solar geoengineering in the model again, it brings it back to what it is now, or kind of normal. So you can play around on that reflective.org simulator if you like, and just explore things. That's the reason for the tool. So what might this have? What implications might there be for rainfall and rain enhancement? We know that rain enhancement and cloud seeding does rely on existing atmospheric moisture, and we do know that greenhouse gas warming will increase the moisture content of the atmosphere generally because of Clarius-Clapeyron, and also because the oceans get warmer, so you have more moisture flux from the ocean. Solar geoengineering will reduce the warming rate of the atmosphere and ocean, and will reduce the amount of moisture in the atmosphere that is available for rain enhancement. So solar geoengineering might reduce moisture availability and therefore impact the efficacy of rainfall enhancement compared to if there were no solar geoengineering. But, and this is a bigger one, oopsie, there's a ton we don't know, and both of the speakers before me, Jean-Francois, said that we need to do a lot of research because we don't actually understand the regional implications of things. So rain enhancement depends on several atmospheric variabilities, not only temperature, or variables rather, not only temperature. There are regional differences due to different circulation characteristics, and that was touched on in the talk before me. Then also in climate models, there's high uncertainties, so the robustness of you need to have a multitude of climate models when you are starting to draw conclusions that could actually have policy implications, and you need to figure out how to deal with uncertainties in models and how do you get your robust messaging. And solar geoengineering might reduce regional moisture availability and impact the efficacy of rain enhancement compared to if there were none in some region, and that might be a different message for a different region of the world where maybe solar geoengineering would be beneficial in the context of rain enhancement. So there's a lot we don't know. There's a lot of research that we still need to do in this space, particularly to understand regional responses to greenhouse gas warming only, but also to solar geoengineering. So let me conclude by saying that we do understand through Clarius-Clapeyron that there will be more moisture in the atmosphere as a result of anthropogenic emissions and global warming. We also know that solar geoengineering can reduce warming rates and warming, and therefore this will reduce the amount of moisture available in the atmosphere. And therefore, it may reduce the efficacy of rain enhancement, and I should have put there in certain regions, but it might also enhance the efficacy of rain enhancement in other regions because it's going to affect regional circulations. Whoopsie. However, there's still many uncertainties, many research questions that need to be addressed, particularly our understanding of the regional impacts of both global warming and solar geoengineering at that regional scale on rain enhancement. With that, thank you very much, and I'll hand it over to the chair.
Thank you so much, Dr. Leonard. Witnessing the depth of your presentation make us be sure that there is no doubt that that invite was for you. And we now move to the panel discussion, where our esteemed experts further explore the topic of limited area climate interventions for rainfall enhancements. Please join me in re-welcoming our three presenters back to the stage, along with the moderator, Dr. Dion, member of IREF's Strategic Direction Committee.
See if this is working. Yes, it's working. Good morning, everybody. I'm very glad to see that there's still quite a few of you around because we've had quite an interesting session this morning, and I want to thank Jean-Francois and Oliver and Chris for their presentations and the insight they have provided us on this very complicated topic. I think we must always remember, because we're busy with life and we must think where we are. We're in 2025, and we think about many of the climate targets and things. We're getting dangerously close to this 1.5. We're getting dangerously close to 2030, which is a landmark year in many respects, also for the Sustainability Development Goals. We are halfway between the year 2000, which feels like the other day, and 2050, which is a milestone year also in terms of climate issues. So it's sometimes important to sit down and just think where we are. And it's no wonder that we discuss this topic even in this forum today. It is clear that there are many questions. I have a lot of my own, but I will start asking Jean-Francois the following. Considering the potential of marine cloud brightening to enhance rainfall over the UAE, what are the critical uncertainties or risks in applying this method to an arid region with the specific atmospheric dynamics that we have here, including the high load of aerosols and all the rest?
Yeah, and that's a great question. So, as I tried to indicate, we're at the level of being able to ask the question and being at the level of, is it even reasonable to expect that such a modification would help the conditions over the Arabian Peninsula? Some of the uncertainties that we have at this point is, I would say, on the knowledge of just the background state of what the aerosol load is over the ocean. We have a reasonable understanding of what it is over land because we have measurements, and we've had measurements for many years, but over the ocean we really don't have an understanding of what it is now, and maybe especially after the changes in the ship emissions, because that changes the overall amount of aerosols. Overall, there's still a huge amount of uncertainty, and I think all three of us have mentioned that, on the cloud microphysics, on understanding how aerosols are formed and how they evolve over time. So understanding that from first principles, being able to do that from the observational side in the area of interest, I think is a critical portion of the uncertainty, and then translate that into models that we can use for understanding over scales that would be sufficient. One thing that I think all of us are showing is that even though this might be like a regional forcing, it will have implication beyond the area of forcing. So understanding how that projects into something that's regional or maybe even global in scale is critical.
Yeah, I do agree. Oliver, could you give us some insight on the following? You've identified through your simulations that significant rainfall increases could be possible from artificial surfaces. What are the techno-economical and environmental trade-offs of implementing such large-scale heat islands? And I just want to add a question that also came from the audience. Would it be possible to install this type of intervention in mountain valleys to leverage the uptake, the upslope wind? And also, what are the most cost-effective technique to lower the albedo? If you could cover that. So I'm tough on you this one.
Yeah, that's quite wide-ranging.
The techno-economical and environmental trade-offs and this issue of the upslope in valleys in the mountains.
Yeah, these are great questions. I mean, of course, with this kind of a project where you're looking at something 10 kilometers or more in scale, this is a huge investment for a start, and it brings with it a whole load of risks and trade-offs as well. For instance, impacts to the environment and impacts on society around. Is it going to affect the local villages or people, and temperatures and so forth? And all of these have to be considered. We also have, looking at the total climate system, you're lowering the albedo rather than increasing it. So this has to be taken into account. One kind of techno-economic trade-off that I can think of is if we weigh the uncertainty of whether it's going to work against the rewards which potentially you could have. And one of the problems is that, as I was mentioning, if you do some measurements over a small area, for instance, we did some measurements in this 2-3 kilometer plantation of jojoba, and we got a huge heat bloom over the canopy of 4 degrees compared with the surrounding desert. I mean, this is a huge, inside the canopy, nice and cool, but on top you really got this heat bloom. However, if you try to extrapolate this to what would happen if the area was much larger, you're running into problems there, and you're making assumptions. I think it's still worth doing, but I think what I'm trying to say is that you cannot just scale a project up like this, look at your measurements, say, okay, this is going well, let's do it more, and so forth. You're not going to get a little small cloud appearing over a 1 kilometer prototype. And this is something which really we have to try and close this gap with better simulations, and as new areas appear which look like good for measurements, then we can try to utilize those. For instance, very large solar farms, and these aren't really now 6-7 kilometers, even more in scale. I'm itching to get my hands on some measurements inside solar farms to have a look at those as a possibility. But yeah, that uncertainty is a really big one. The other one, I get asked the question, you're heating the desert, are you crazy? And which is really a fair question. I mean, if you get advected warm air going down to the next town or village, this is a real concern. Actually, in the last paper we did, we looked at the temperatures, and actually the temperatures mixed out fairly quickly, and they didn't advect too far, at least close to the surface. But of course, this has to be seen in the real world, under all conditions, but it's a very real possibility. The last part about the forcing, so of course, a 10 kilometer or larger area, you're reducing the albedo from 35% to 5% or whatever it is. Yeah, this just has a measurable effect on probably on the global forcing. Okay, a very small one, but it's definitely a trade-off. Of course, we're not taking into consideration hydrology, effects on the cloud feedbacks and so forth that have to be looked at. But I think the next question was about cost
it's all about, as we know, most of the clouds develop over the mountains to the east.
Oh, yeah.
And so the valleys there might be an attractive place to try and make some intervention. So what are your opinions on that, and would something like that be possible?
Yes, definitely. I think, yeah, I pointed out one of the weaknesses of the index that we did look at before was because where you have orography going over the top of the variables you want to measure, it doesn't really work very well. I know most of the clouds occur over the Al-Hajjah, and I think that would definitely be a possibility to put them in the valleys around Al Ain and or Fujairah, and definitely local knowledge from local meteorologists would be ideal for this. You know, I mean, as you know, we did some measurements with radar and lidar at the weather station, Fujairah TV station, And we got some fascinating results on convergence lines occurring in valleys, and we could really see where convection was about to occur. And so definitely I think this could be combined. I don't see any reason why this couldn't be combined here.
Okay, so for Chris, your presentation suggests that solar radiation management could reduce the efficiency of rainfall enhancement programs by altering atmospheric water content, as you mentioned, through the Clausius-Clapeyron equation. Could you clarify how these interactions might differ between local versus global applications of this technique? I think you've shown some of that in your presentation as well.
Yeah, the global versus local is the question. We understand by first principles the global response to SRM and what it would do. But understanding the local response is very much the challenge of both. You can't do stratospheric aerosol injection for a local response. That's not appropriate. So anything you do in the stratosphere is going to be global because it distributes across the globe pretty quickly in the stratosphere. But then local interventions, Jean-Francois mentioned what's going on over the Great Barrier Reef in Australia. And here, the idea is to just try and cool the ocean around the Great Barrier Reef because they're losing tons of biodiversity through coral bleaching and then all of the animals that rely on the corals in that region. So if you are able to cool the ocean by 1 or 2 degrees in that area using some kind of marine cloud brightening technique, then you're doing something local. But is it really local? Because both speakers mentioned what are the downstream effects of my local intervention, because nothing is really local. The atmosphere is a chaotic atmosphere. What you do in one place will have an effect in another place. So when we consider these types of interventions, we really need to consider the entire atmosphere holistically. So you got to span the full scale from the full globe all the way down to the local scale. And just riffing a little bit on what you were saying, is that at the local scale, instead of putting dark blocks, can you put in light blocks? I'm just thinking of that days above 40 degrees that you would experience 25 more days above 40 degrees in the summertime. Is there some way of investigating, could you cool things locally by putting in white blocks? So if the desert is, what did you say, 32% albedo? Can you put in blocks that have a 70% albedo and maybe that creates cooling? But again, that will influence the local and regional circulation patterns probably. So the research questions are really key. So to try and understand what the global, regional, local effects might be of these various interventions we're talking about.
Yeah, and of course, it's not just like equilibrium state with Clausius-Clapeyron. It's about invigorating the whole hydrological cycle. So we need to think about evaporation, evapotranspiration as well. That goes hand in hand with these other things. So when it's cooler, you have less of that again. So it really makes me think that the human race is really clever to systematically paint itself into a corner and then create these very complex problems that they then try to solve through research. And it's very clear that in this field there's a lot of research still needed. And I think the central message here is about capacity building, research, addressing fundamental questions, because if we look at the climate projections as we go forward in this century, the things that are most uncertain are the things related to precipitation. And now we talk in the context of this forum about how some of these techniques can address that issue. So for me, the central theme here is we need to better understand how the atmosphere works, and hopefully the pressure on the climate system and these type of suggested interventions will stimulate more research to address those fundamental questions. But I would like to ask each of you to just indicate in terms of capacity building, what do you see the needs? Because I think it's quite a complex issue that deals with things right from governance, building of trust with neighbors, diplomatic skills, scientific skills, technical skills. Because at the end of the day, you get down to the issues of modifying clouds or modifying the atmosphere, and then it's basically the same questions that many in this community has been battling with for many years. So it's that additional complication at that very low level as well. But higher up, there are many other things that come in here. So please enlighten me and the audience on your thoughts on that. Let's start here, yeah.
Okay. So I think that's an extremely relevant question, and I think this is also where being part of this group is very relevant. A lot of the questions that we are receiving on the validity and the importance of looking at solar radiation modification are similar in tone, in my mind, to the weather modification issues that people are looking at here and have looked at for many, many years. So we can really learn from experience on what actually needs to do on the governance, on trying to bring these discussions to the level where they should be discussed. I think your point is also very relevant, that there might be the tendency of looking at it from a very global picture, very global scale, very driven at this point by the people who have access to enough computing power to ask the questions. And I think we really need to bring the capacity and the capability to the people who actually would be most impacted by those activities. So I think being able to bring those tools and defining the new tools that would be useful for community like around here or anywhere in around that would be affected by those choices is really critical. I think the main point, and I think Chris was just mentioning that, is that local knowledge is going to be critical. At some point, there is only if we have a full understanding of how the world functions, and in this area, that we can actually trust any projections that we have into the future. So building capacity, building the workforce, make sure that there's full interaction, full collaboration, like this program of bringing people from all around the world with all their experience, and is actually really critical to see if the kind of things we're discussing here should be viable options.
And I think it's not just the local knowledge of how the world works here, but it's also how the people work here and how the culture and all those
absolutely.
things. Really important. So can we get more insights from you two?
I don't know, you put it very eloquently. I agree with a lot of that, especially with events like this and IREF, and this is just a fantastic way of trying to get this information across to people on a scientific level, but also with journalists and really advertising to get the simpler messages across, which are also necessary for other people who are not working in these specialist fields. And I think a good case in point is this kind of mishmash mix-up of geoengineering and limited area regional geoengineering. Semantics also plays a big role here, and people are getting things mixed up, and particularly with geoengineering, where I think 90% of the research goes into stratospheric aerosol injection, or at least that's what I see, and this is what everybody focuses on, but there are many more possibilities and options as well, and I think this really needs to be categorized better, and that there are other options out there, that it's not a dirty word. And I think, just making things clear, and really education plays a big part in that, but we also need to decide and get our ducks in a row and give things the right terminology. And
No, I think if there's a field where scientists need to be sensitive and responsible, it is this field, in how they communicate and how they go about to talk about it and promote it or not promote it, or It's important stuff, and we really need to make sure that we ensure that scientists are there to make the world a better place, and this is all this is about, despite the many questions we have. So thanks, Oliver. Chris?
We're doing this, so our speaker is an African-based researcher now, and we're trying to build an African research community in doing SRM research. That's both the stratospheric and marine cloud brightening and also some other things. And we are building on a very small community, but there's probably now about 15 or 20 researchers, leading researchers in Africa looking at this theme, but it's very part-time. It's like maybe 10 or 15% of your time that you can give to this research. And then we have students and postdocs. So all in all, within Africa, we're building a community of probably about 80 folk, 80 or 90 people who are researching SRM in the physical science space, but then also in the social science space, because SRM is not just about injecting particles into the stratosphere or trying to brighten marine clouds. It's also needing to think about ethical questions around doing this type of work. It's about how do we address governance around this. If God forbid, we ever have to go this route because we find the impacts are really bad, how are we going to govern this? So we want to, as Africans, actually put our perspectives forward. The Europeans will have their perspectives, the North Americans theirs, every part of the world will have its own perspective, and we want to prepare the African perspective on this, because I think if you speak to any of us in this field, as the impacts of climate change and global warming get felt more and more, particularly by the global north, as it starts to cost them more money, as more global north folk suffer the impacts of this, as we breach 1.5 degrees by early 2030s, and then we're going to breach 2 degrees in the 2050s, the impacts of this is really we're going to start feeling them. Well, in Africa we're feeling them already, but the global north will feel it. And this is probably the only intervention that one can do quickly to try and reduce some of the impacts that we feel as we continue breaching these different thresholds that have been set politically, for whatever that means anyhow. So we have to understand what might happen, and in Africa that's what we're trying to do. We're trying to build this research network to understand how do we respond at a political level to this thing, as I think it's going to become more and more of a discussion point over the next 5 to 10 years.
Yeah, because it's unavoidable. It will be a discussion point, and so I think it's really important here that regions also learn from each other.
Yeah.
And it would then be important that centers like you talk about then interact with centers in other parts of the world to build the capacity around these topics. We've got a few questions from the audience as well, and maybe the first one, Jean-Francois, I'll address this to you. As we know, we already have very large volume of aerosols in the form of airborne dust in this part of the world. What difference would it make to add sea salt? Of course, many of the particles in the atmosphere also, there's some sea salt components already in there.
Mm-hmm. Right. So that's a big question. I think the way I look at the potential of using changes in aerosol distribution as a way to drive circulation changes is that most likely you would be doing that over the ocean, not over land. So I don't know how much of the dust that is present over the land areas would actually be transported. I'm not familiar enough with the circulation around here. But so dust is a very good, well, it's a better ice condensation nuclide than a CCN. Sea salt has more potential in affecting the cloud distribution and the radiation. It's much more reflective, has a better way of interacting with radiation than dust has. So I think there's more potential in the use of sea salt, but it is, and that's where we have to understand what are the current conditions. But you can still think of it Because here we're talking mostly as a radiation effect, right? So in essence, there's probably not as much a saturation issue the way you might have in the cloud aerosol interaction. At some point, adding more aerosols is not going to change the CCN and the distribution of cloud droplets. You just saturate in the impact. In terms of radiation, you're not as limited. So, but understanding where you are and how much you need to modify it, I think it is the critical question that I think we need to identify before we do much more research on the topic.
I think this question was specifically more related to the radiative effects than the role in clouds through CCN and ice nuclei. And we know that we've got local dust sources, but also regional dust sources. So if you fly over the region, you can see the dust haze really blankets the whole area, whether you're over the ocean or not. So it's a relevant thing, and it probably needs more observations and a better understanding regarding sizes, chemical composition, and so forth. And this next question makes me think about a study that was done many, many years ago related to St. Louis and how that city impacts on the atmospheric circulation and cloud formation around it. And this question is on cities effectively large-scale heat islands. There are also perturbations to roughness. We also know that there are sources of aerosols and other things that change the atmospheric chemistry. Do they stimulate convection and or rainfall? So maybe, Oliver, this one is for you again.
Urban heat islands. Yeah, there's definitely some parallels between this idea and urban heat islands, but there are also some critical differences. Firstly, yeah, it's been well simulated that large cities do have an effect on the convection. Stuttgart, for instance, where we are, is definitely a source, especially at the lee side of the city in respect to the mean wind direction. There are definitely downstream thunderstorms more likely to occur. There's plenty of other studies in Tokyo and where this happens. Of course, there are regional peculiarities, whether they're on coastlines and so forth. This does have a huge effect. I would say some of the differences, urban heat islands have a large storage component so that the concrete and structures are really heating up, and a lot of the heating is really occurring later in the afternoon and extending into the evening as well. And with this CPR, typically there's less storage, I would say, so that most of the heating really follows the kind of radiation peak. So most of the heating would occur during the middle of the day or just after. So this is definitely a fundamental difference, I would say. But the effect is similar.
Okay, and then Oliver, another one that you could maybe just shortly give some better insight. I know that you touched on the characteristics of a jojoba plant. We do know that they will darken the surface, but this issue of evapotranspiration that would then offset that. Just explain to us again a little bit more around that.
Did you say offset?
Yeah, because the evapotranspiration will then have a cooling effect again.
Yeah, that's a great question. So we did lots of measurements on this, yeah, in Beersheba in Israel, in some jojoba plantations, and we also discussed a lot with the agronomists there, the world leaders in drip irrigation. So we had a really good insight into how the plants work, and really these certain type of xerophyte plants, they can really try to avoid losing water by really closing their stomata in the middle of the day. And very often the leaves are vertical or have a waxy, and they can really photosynthesize mostly during the early part of the day and the later part of the day. And they can really shut off in the middle of the day when it's too hot. And really you can see this in the heat flux. In the middle of the day you get a very strong heat flux, but the plant's perfectly okay. It's not losing water. So then we come on to the irrigation. The plants do need some water, of course. Jojoba needs around about 700 millimeters a year, something like that. So there is a bit of evaporative cooling. Nevertheless, when you take into account the whole energy balance, you can get maybe 150 watts of latent heat, but still get 300 watts of sensible heat flux. So the plant is transpiring, it's working, but you do get a strong sensible heat flux. If you're putting maize plants in there, these are evaporating very strongly. If they have enough water, yeah, it's going to be cool, that's for sure. But jojoba and other similar plants, which are really desert plants, they can work in a different way. So, yeah.
Thanks for the insight. So, Chris, considering the current gaps in understanding the atmosphere flux changes induced by solar radiation measurement, what research priorities should the scientific community focus on to address these uncertainties?
I'm going to sound like a stuck record and say we really need to understand the regional impacts of climate change and the regional impacts of climate change and SRM. So it's very much, again, saying what Jean-Francois was saying, having the expertise at the local and regional scale to really inform the research questions is critically important. I think we struggle to get to the correct research question, and that is very likely the most important thing that we need to do in this space is try and figure out, for me in my region, but then also, as was said earlier, this is also a global picture. What are the critical research questions that we need to address? And I don't think we know that yet, because the modeling centers are running models, which is what they want to do, but they're not running models to address a question. So I think getting to the right questions is what we need to do in this space over the next couple of years, and then addressing those questions to inform policy, because this is going to be a policy discussion within the next 5 years. So to inform policy, what are the questions that we need to address in our particular regions?
Thank you. We need to wrap this up. We're running into the coffee time, so it's clear you have sent a very strong message here about frameworks that cover many issues relating to ethical, sustainability, scientific, technical approaches, cooperation, capacity building, a lot of questions. It's innovative work, but it's still very experimental, but it also puts additional pressure on the atmospheric and climate scientists there, because the questions that need to be answered to also make this technology a viable solution for the future are many times the same questions we have in terms of human-induced climate change out there and the models that we use for that and the understanding. So I want to thank you for sharing your insights, and I would like to congratulate you in the normal manner.
Let's give our panelists a round of applause for their engaging discussion. And we will now take a short 10 minutes coffee break. We'll get back at 12 p.m. Apologies for the misreference. I'm pleased to invite Abbas Karim, General Manager Fluid Codes, for delivering the opening speech.
So good morning or afternoon. It's an honor for me to open the 6th session of the International Rain Enhancement Forum here in Abu Dhabi. So this is a focus of the session is on new approaches and innovations for cloud formation and rainfall enhancement. So today we'll hear from innovative speakers on their ideas and insights into how new technologies can help us tackle the challenge of water security. So as introduced, I'm Abbas Karim. I'm actually specializing in simulation technologies. So I'm looking to talk to you a little bit about how simulation can help in this kind of challenge. So there's supposed to be slides, but not sure if they're... Okay, we can talk. Do we have slides or no? No? Okay, fair enough. So I was Robert earlier, but also I don't have slides, but I'll try to talk to you a little bit about what I wanted to kind of convey in this opening. So the need for these kind of new approaches is very important, with water scarcity being a critical issue, and traditional methods like cloud seeding are having its own challenges and issues that need to be kind of addressed in terms of efficiency and effectiveness, as we heard this morning. So particularly in the Middle East with these harsh conditions and harsh environments. So there's a need for leveraging emerging technologies like directed energy, like nanotechnology, and my area of expertise, which is simulation. So building on the needs of these new approaches and these innovations that are required, if we look at some of the typical kind of applications, chemical cloud seeding, UAE has been a pioneer in this field. But obviously, this is one particular type of innovation. There are also infrared laser pulse technologies. This has been tested in Berlin, Germany since 2010, and this looks to be an innovative kind of approach that could be applicable in this area. And there are also electric charges approach as well. So since a few years, UAE has been also applying this technology for this challenge. So if we look at some of the kind of new approaches for cloud generation, so if I had the slides, I could have shown you a few examples of those. But typically the cloud generation type of technologies, they are quite expensive. They're not really proven and not scaled up to be tested in kind of in a real environment. So what we're talking about here is how can simulation help us answer various questions around cloud generation technologies. So in other words, where can this technology work, and when can it work? What are the atmospheric environments that can help it work? So I'm an advocate of engineering simulation. So engineering simulation is applied in many fields. So I work here in the UAE in terms of applying these approaches to different technologies and different applications. And it's essentially a mathematical representation of the physical world. So this is not new. The mathematical representations are not new, but computing power has excelled so much today and in the past decade or so, such that these technologies can be applied into more and more complicated applications. So it's a shame I cannot show you the slides, but we have some examples of, for example, cloud formation using tower approach. So using simulation, such an application can be tested to answer this exact question. What time of day and what environment condition is required to enable the cloud formation to happen? And this obviously allows engineers and scientists to be able to test innovative ideas. And then in the area of directed energy, so outside you can see some of the applications from Technology Innovation Institute, where development of laser and directed energy applications could potentially be used in this application. And essentially simulation can help us get to that point faster. So to conclude my talk and to introduce the kind of next speakers. So obviously the importance of new technologies and ideas in solving water scarcity issues is very important. And the upcoming speakers are going to be talking about some of the different innovations and to some extent using simulation in that area. I hope you enjoy those talks and you can see how engineering simulation could potentially help in that area. And I thank you for your attention, and thank you again for the organizers for inviting me today.
Thank you, Abbas Karim, for your inspiring remarks. Dear audience, as usual, we will be taking questions to our upcoming presenters during the panel discussion after all three presentations are completed. Please be sure to submit your questions using the QR code and our moderator will address them. Our first presentation in this session will be delivered by Kala Golden, Cloud Seeding Program Management at the Idaho Department of Water Resources.
All right. Well, good morning, everybody. I'm very thankful to be here this morning. As many of you, I'm quite honored by the opportunity to be here and collaborate with leading experts in this field. And so, again, my name is Kayla Golden, and I will start by saying that unlike many of the folks that you've heard from over the last few days, my background is not really in the technical realm, but rather in the oversight and management and the collaboration between our operators, our governance, and our research. And so that's largely what I'll be talking about today, is how our programs have evolved on what I call sort of the three pillars of a triangle. So to start with this presentation, I'm going to set the stage by really providing an overview of cloud seeding in the United States, not just in Idaho. And so looking at sort of the geography of Idaho, this helps explain, why we have different types of cloud seeding across the U.S. And so what you'll notice is primarily in the western half of the U.S., the areas that you see with that blue shading are where we conduct wintertime or glaciogenic cloud seeding. And if you look at the geography on the map, that is largely due to the complex mountainous terrain of the western region of the U.S. Moving over into the middle portion where you're seeing some of those green areas are both hail mitigation and rain enhancement projects that operate in the warm season. And so in the United States, we do have both, given our large geographic area. But today I'm going to focus in primarily on Idaho and how we've grown. So I guess another aspect of setting the stage to this is to really take a look at sort of water use in the United States, which drives why we have developed some of these cloud seeding programs. And so what you'll notice, is that a large portion on the western half of the United States is covered in green, where the majority of our irrigated agriculture is. And so as many of you are aware, the U.S. is one of, if not the largest exporter in agricultural goods, anywhere from $150 to $200 billion in exports on an annual basis. And all of that relies on water supply, so it's a very significant amount. Like many of the talks that you've heard over the last couple of days, we are equally facing some of the impacts of climate change, seeing increasing demand and diminishing supply. That is largely attributed to growth in population. We've had a lot of growth in technology, particularly in our state, and all of those things require water. And so how do we manage those complex systems across a variety of different industries? So zoning into water use in the United States, these numbers are slightly outdated. Unfortunately, we don't have a comprehensive evaluation of current use, though that is something that we are working on, but it is still pretty similar in that what you will notice is that a large portion, upwards of 90% of the water use in the state of Idaho is from agricultural. And so more of that, we do rely on aquaculture and industry as well. Over the last probably decade, I would say, we've seen exponential growth in technology as well, with folks like Meta moving in, large data centers that require water as well, obviously for heating and cooling. And so then with that growth in technology, you also have a growth in population because you need people to work these jobs. And so then you're considering large population growth coupled with technology growth, coupled with existing demand for agriculture. So some of the other things to consider within the state of Idaho is that, we don't only look at the consumptive uses of water. There is significant value to a number of different industries within the state of Idaho that rely on water that are not necessarily consumptive use. And so when we're looking at declining supplies, we're not just evaluating, how that impacts our ability to use water, but also how it impacts a variety of different industries that don't use it consumptively. So one of the big ones that I will talk about is hydropower generation. In Idaho or in the western United States, we have some of the cheapest electricity rates. A lot of that is due to our hydropower generation. It is the largest contributor to electricity, at least in the state of Idaho. Adding to that, the state of Idaho is a four-season state. So we have mountainous terrain, we also have arid deserts, we get warm season, cold season, and we have a significant amount of recreation that supports our economy. And that is all reliant upon water as well. And so taking that a step further, we have a significant amount of very important fisheries and wildlife, many of them who have some level of endangered categorization. Adding on to that complexity of a variety of different industries and uses of water is the complexity of water law in the United States. And so lots of administrative boundaries create lots of complexities in managing water, and I often like to repeat myself in saying that, we know water and weather don't follow administrative boundaries, and so managing water and managing programs becomes infinitely more complex when you have a number of different administrative boundaries. And so water in the United States, each state has sort of some of its own policies. While there are some federal regulations and guidelines, water is generally managed at the local level by individual states, which, as you can imagine, across large watersheds where you have interconnectedness between states, creates significant complexities in administering and managing those water supplies. So in Idaho, not only are we managing surface water supplies, but we're one of the only states that conjunctively manages both surface water and groundwater. And so, again, considerable complexities that we have to manage. And so to really take a step back and look at the characterization of Idaho, compared to some of our our warm season projects, complex mountainous terrain, winter orographic clouds, which is why we conduct cloud seeding in the winter, and stream flow driven by snow melt. And so I know a lot of folks will immediately take a look at this image and go, wow, what is the issue? You know, we're a very water-rich state, and unfortunately, what you'll also notice is that we're not a closed system. Water enters and leaves the state on both sides, and we have a significant amount of industry that relies on that water as it flows through our state. And again, as I mentioned, that goes beyond our state, beyond our borders, as you know, we have a significant amount of exports and industries that rely upon our state worldwide. And so how do you manage a water supply to support a broad number of industries? So this timeline really doesn't capture the entire history of cloud seeding in Idaho. It's more focused on the state's participation. But cloud seeding really began in Idaho in the early 1950s, very shortly after it was demonstrated in a lab setting in the 1946. And so most of our projects were very sporadic, start and stop. If you overlay that with some of the drought periods over the last several decades, the starting and stopping of those projects is pretty consistent with drought and water supply availability. So generally when water supply was good, folks didn't feel the need for cloud seeding and we didn't see a lot of projects operational. However, when we moved into drier or drought periods, all of a sudden there became funding. And all of those programs, basically through the first 5 decades of operations in Idaho, were funded locally by private stakeholders within the basins where cloud seeding was operated. And so really the nexus to that was that we have a large power company with significant investments in hydropower, and they had an interest in producing more water for hydropower generation that supports their long-term clean energy initiatives. And so what happened was in the late 1990s, Idaho Power Company began investigating cloud seeding as a mechanism to support hydropower. That water is not only significant to the power company for hydropower generation, but in the state of Idaho, we obviously have large forested areas. And as we've heard, you know, time and time again with a changing climate, we are plagued quite significantly by wildfire, and the power company having large infrastructure across varying territories across our state. You know, having hydrated soils and forested systems to help prevent any potential impacts or contribution to wildfire is significant on another level as well. And so, again, going even further to the complexities. And so, starting in 2003 was really when the power company began its initial operations in the Payette River Basin of Idaho. That was the first time that we brought remote ground generators and aircraft into the state of Idaho for cloud seeding operations. So the power company really was operating from about 2003 to 2008 when the state began some large-scale investigations related to our comprehensive aquifer management planning. And so I guess maybe to take a step back, that it would be helpful, what you notice on the southern part of Idaho, what I call our Idaho Smile, is this large area that is not covered by mountainous terrain, and that area is what we call the Eastern Snake River Aquifer Plain. It is one of the most fertile aquifers in the entire world. And so fast forward to the state's involvement in 2008, you know, why did we get into cloud seeding? The reality was that we had a declining aquifer that supports about 3 million acres worth of irrigated lands. And so just to give you a brief background or history, if you look at a graph of the water supply availability in that aquifer starting in the 1900s, we see basically a perfect bell-shaped curve from the 1900s to about now. And the reason for that is that, you know, we had artificial recharge going on in the early 1900s as a result of flood irrigation. Move fast forward to the 1950s when we started pumping irrigating, and then we started declining from that aquifer. Moving forward, we've tried to make advancements and efficiency improvements to our irrigation, which further reduces flood irrigation and some of that artificial charge that goes into our aquifer. And so these issues just continued to get infinitely more complex, but largely, why did the state become involved in cloud seeding? It's because we have an aquifer that has significant value to a number of different things. So in 2008, we basically came to a headway with stakeholders, the state. We recognized that the aquifer was declining and that action was going to be necessary to prevent significant impacts in the future. And so going back to the power company who had started cloud seeding another basin in 2003, this same power company has hydropower investments along the eastern Snake River Plain. About 17 in total hydropower generation projects along the main stem and its tributaries. And so basically what happened was the power company came to the table with the state and said, well, we have experienced cloud seeding in the Payette, maybe by cloud seeding in the upper Snake River Basin, we can add water to sustain this aquifer. And so that was really when the state first came to the table as a participant in cloud seeding within the state of Idaho. And so really the idea when they came on was that the power company would conduct a 5-year pilot project, and if successful, the state would move forward through a collaboration with the power company and local basin stakeholders, water users within those basins, to fund and collaboratively manage a cloud seeding program. And that's exactly what happened. So Idaho Power, we did find success in that program. And that was really the inception of the growth of our program from that point. And so 2015 was the first time that the state made its initial contribution into cloud seeding. And that was really just a small, relatively small contribution to capital investments into this program. And so when the state made this first investment, that was just a few years before the Snowy Field campaign or some of the groundbreaking research that really demonstrated the efficacy of glaciogenic cloud seeding. And so that star is noted right there, that blue star on the timeline, and what you'll notice from that point is significant growth in our projects and programs from there. So I'm not sure how many of you have seen this model. I thought maybe it would be helpful just to demonstrate, the conceptual model of glaciogenic cloud seeding, as largely we've discussed warm cloud seeding on this side of the region. And this image is put together by the National Center for Atmospheric Research in the United States. And basically the goal of winter orographic seeding is to increase snowpack. So snowpack in Idaho and in many of the Northwest Territories is our primary water storage reservoirs. And for a significant amount of these states and areas, we are seeing declining snowpacks and earlier melt-off, which has a significant impacts for a lot of different reasons. And so in Idaho, we use a number of different types of equipment. Like I mentioned, we started with ground generators that started as a manual generator, and we have upgraded to remote generators. So with this conceptual model, these generators are placed on the windward side of a mountain, relying on orographic winds to take silver iodide seeding material up into the cloud, where it can nucleate ice that will eventually fall out as snow and melt off. So looking at our cloud seeding operational infrastructure, there's a number of different components to support our program. And so the first and foremost being forecasting and operational guidance. So in the state of Idaho, we use the WRF model, the Weather Research and Forecasting Model, coupled with a WRF-based cloud seeding model to guide our operations. That is not something that we use in real time quite yet, hopefully in the future, but a ways to go. We then have a very large weather instrumentation network. And so one of the complexities of being in a mountainous terrain is that you have large blockage areas, right? And so particularly when it comes to radars, there's a lot of areas where we have instrumentation needs to support these programs. And so those are one of the major considerations in growing our projects and programs, is that we have to have, weather instrumentation to guide our networks. And when you have these mountainous terrains, you get a lot of sub-regions, and that creates a lot of complexities in understanding weather to guide and operate wintertime seeding. So in terms of our ground operations, we presently have about 52 remotely operated ground generators across the state. Those are silver iodide based ground generators that release a solution. Again, we place those on the windward side of a mountain, and those are remotely operated. And then we rely on winds to take that material up. So the challenge with remote ground generators is that they are stationary, and weather can often be dynamic. And so in addition to ground operations, we also operate with aircraft. And so 3 of them in total across the state. These are certainly the most costly portion of our project operations, but they allow us to be flexible in targeting different areas of the storm depending on where that supercooled liquid water content is. So focusing in a little bit closer onto some of our operations, I recognize this map is just a little bit busy, but we generally have 2 different regional areas where we operate in the state of Idaho. The first one being what we call the West Central Mountain region, or the Central Mountain region of Idaho. And I've zoomed in on that project here. And what you'll see is that within this regional project area, these areas outlined in red are again administrative boundaries. And so those are hydrologic basins that are managed individually by water districts in those basins, and water users within those basins are assessed fees to manage the water supply in those basins. Additionally, water users in those basins are assessed fees that are contributed to their cloud seeding operations. So it is sort of a 3-way partnership, in that we have the state as sort of the government body helping to facilitate the operations. We have a private operator, a company who has made large investments into growing a program, and then we are supported by the local constituents of stakeholders who really rely upon this water. And so what you'll notice is that, there's a lot of cross-hatching across this. These lines are aircraft tracks, and they cross over the basins. And the reason, again, going back to this idea that water and weather do not follow administrative boundaries, that is the reason that we operate our programs more on a regional basis. And so they are funded, by basin. So each individual basin provides a certain amount of funding to contribute to cloud seeding operations. And to make that financially sustainable, what you'll notice is that there's a lot of infrastructure along the divide, noted by some of these crosses, and then overlain by aircraft tracks that go across all 3, is that we share infrastructure. And so infrastructure can be set up and designed to support a region, while allowing a cost sharing of that financial burden between our water users. And so that is very significant, and that has been a very significant contribution to the growth of our programs, and a large reason why we have been successful in growing to this scale. So again, looking at the Upper Snake River Basin, this is where the state really began investing, particularly in cloud seeding, was to support that southern smile of Idaho, or the Eastern Snake River Basin aquifer. This basin is a lot larger geographically. It has about half of our ground generator network, and 1 single aircraft. And so this basin does have a significantly higher financial burden, as presently it doesn't share costs with some of the other basins. And so for the state, trying to understand how the state can equally support water users, given it has an obligation to support water supply across the state, again, becomes infinitely more difficult and complex. So thinking about some of our operational considerations, I did briefly mention already, our weather instrumentation network, and the complexities that we have due to mountainous terrain and large gaps in data coverage. Looking at our ground operations, even to develop ground generators. So in the United States, for example, there really isn't an existing entity who develops these. And so most of our ground generator infrastructure has been developed by individual programs or project operators who conduct cloud seeding. And so this is very significant for other states in the United States who are looking to grow projects and programs. Where do we get these resources when a lot of the instrumentation and the equipment that we have has been developed for specific programs? Going even further, siting of equipment, again, we go back to the administrative boundaries. Trying to place equipment in these higher elevation areas, or generally federally regulated areas, or forested, either managed by U.S. Department of Forestry, Bureau of Land Management, and so that requires us as a state to collaborate with federal entities, or a number of different entities, to even get our instrumentation in place. And so, as a lot of us have talked about over the last several days, there's significant amount of communication and collaboration that has to happen for that, in addition to the fact that siting these in high mountain elevated terrain requires, land access. So there's a lot of complexities even trying to get the generators into a site, let alone getting the permitting or the authorization to put them there. Looking at our aircraft operations, you know, there's a number of different considerations that we have to consider for wintertime cloud seeding. So, you know, for example, we use a larger caliber aircraft, generally a twin turbo engine. And the reason for that is because when we're targeting these winter orographic clouds, these juicy winter orographic clouds where we're looking for that high supercool liquid water content, these are places where pilots typically avoid, right? Because if you fly through an area of dense, supercooled liquid water, you essentially start accumulating ice on that aircraft at a much faster rate. And so these are very strong considerations is when you're flying in a mountainous region and you need to get up out of a cloud or move your aircraft system to avoid running into a mountain. There's a lot of complexities that get added to that. And so safety and caliber of our aircraft and pilot crew are significant considerations for our programs. Aircraft modifications as well. There's a lot of, you know, regulatory considerations to go with that, as well as efficiency. And then operational guidance and communications. And so every year our project sits down with our operators. We come together for what we call a ground school. And every single year before our operations begin, we meet with our stakeholders and our operators to understand what our operations are going to look like, what considerations we may have, such as suspension criteria, when our snowpack has exceeded, you know, ranges of average, or if we're experiencing rain on snow, for example, things that might contribute to flooding. You know, so going even further, obviously for any program, it requires a meteorology team to constantly be monitoring the weather and our operations. And again, this becomes very significant when we're looking at aircraft operations. So why have we grown so much? You know, I mentioned the Snowy Research Project, that star that was on the timeline, and that is largely because of the research that was conducted actually in the state of Idaho by the National Center for Atmospheric Research. And this field campaign is quite unique in that it was conducted utilizing an existing operational program, right? We didn't come in and bring in and set up an operation for this evaluation. The power company had been already operating in this basin for quite some time. And so from a research perspective, that is cost efficient to partner with an existing program operator. We then had the National Center for Atmospheric Research come in, funded partially by the National Science Foundation to conduct this research. And essentially what they did was bring in a couple of these Doppler on-wheel radars, so the same thing that you see in storm chasers, and about 75 different weather instruments that were set up across the basin, and those are kind of noted in that map in the center, to really capture essentially like a 4D picture of the atmosphere. And so looking on the right-hand side, you know, this image that you're seeing right here is a radar image that was captured during one of our IOP periods. And at least in the state of Idaho and for a lot of the programs in the Northwest, this is something that we consider sort of the holy grail in terms of wintertime glaciogenic cloud seeding. And the reason for that is because it provided the very first unambiguous evidence that cloud seeding could work, that winter glaciogenic cloud seeding could work. And so what you're seeing on this radar image as this image goes through, we'll start right here with this yellow line being the flight track of an aircraft, the red dot going back and forth, and then the ice reflectivity in blue. And what you're noticing is a very unnatural zigzag-like pattern, and that's why I say unambiguous evidence that we saw the ice reflectivity from these operations. And so what you'll also notice in this image is that these lines will go back and forth from solid image right about here, switching to a dotted image right here. And that is due to a change in the type of the type of flares that we use on our aircraft. And so wintertime aircraft, we have both wingtip mounted flares and belly mounted ejectable flares. And the reason for that is it allows us more flexibility in targeting different portions of the cloud. So if an aircraft is flying through a cloud and begins to sustain too much ice to the point where that aircraft needs to pull out to shed some of that, we can then utilize those belly-mounted ejectable flares to start dropping silver iodide into the cloud. And so what you're seeing on this radar image is moving from the wingtip flares being the straight lines, moving to the belly-mounted ejectable flares every 30 seconds. And you can very clearly see that in this radar image. And so that evidence right there was largely what convinced a lot of states, public agencies, and others to begin investing in cloud seeding in the United States. And we've certainly seen significant growth since that 2017 period. And so I would definitely argue that this one experiment, particularly being for a relatively low cost, the impacts of its findings were monumental for the growth of cloud seeding in the United States. So this is just a quick image to show this, again, if you look in this circled corner here, you'll start to notice a zigzag pattern reflectivity. This was captured by a National Weather Service radar during one of our operational periods in the Upper Snake Basin. So further evidence to justify, that unambiguous evidence that yes, it is working. So going back to our timeline, in 2017, while we finally have this evidence, so now what? Well, we are a state agency and we rely on public funding, and that public funding has to support a number of different things. And so cost efficiency of the money that we expend is very significant and very important. And so while the state did not directly participate in funding contributions for the field campaign itself, the state did begin collaborating with the power company, making nearly $2 million worth of investments into taking that data from the Snowy Field campaign and utilizing it to develop and advance our modeling technologies, most specifically Worth WeatherMod. And so in the orange, in that modeling category, that's why you see significant growth from that point. The power company had been using this model to guide operations, but really the nexus for our desire to use it, at least as a public agency, was for evaluation purposes, right? What is the impact of cloud seeding? And you really need to understand that to be able to disseminate the cost efficiency of it. And so the state had to begin making significant investments. Not only that, but given we had seen proof that it worked, we all of a sudden now have, several other basins across the state with water supply shortages or needs who are now, the state is now looking at how can we support and invest in those other basins as well. And so the state has also made significant investments into feasibility and design studies to evaluate how cloud seeding can support the state across other regions. So really, what are the benefits of increased snowpack and subsequent stream flow? And I really like this image because it really does a good job at demonstrating that one single drop of water or one snowflake, can have compounding benefits across a system. And so for us in the state of Idaho, that snowflake starts in the mountain where it provides benefit to recreation. The world's first ski chairlift for wintertime skiing is located in the state of Idaho in one of the basins where we cloud seeding. Wintertime recreation is a very significant contributor to our economy, and so first benefit there. As that snow melts off and starts to run downstream, we get availability of water for our mountainous areas. This is extremely important, obviously, when we're having a drying climate and forested areas plagued by wildfire. That water will continue downstream to contribute to groundwater plant uptake and then moving down into our high elevation streams and into our aquifers. In Idaho, we have a lot of high mountain elevation streams where we have significant fisheries and wildlife. Again, many of them that have some level of endangered categorization that rely on these streams. So again, the added benefit of increased snowpack and subsequent runoff is additional water for these as well. I mentioned the Eastern Snake River Plain aquifer. So again, more water flows downstream, more water for that aquifer. But then you start getting into a large level of complexities, right, because of how we use this water. So because of the significant amount of agriculture, both ground pumping and surface flowing, there is a significant amount of interference between hydrologic connectivity between the surface flowing river and the aquifer. And again, managing that conjunctively becomes infinitely more complex. So what is the value and the benefit? Well, more water on the system benefits all of those things in that complex chain. So moving further downstream, the state of Idaho, we have a lot of storage reservoirs that we rely on for both irrigation, agriculture, and a number of other different things. So again, compounding benefits. That water may be used by irrigation, it may go back into the aquifer, we may have runoff, but it will keep going downstream to support the fill of our reservoirs, hydropower generation down the way, along with a number of different fisheries and water quality. Like many other areas of the world, we definitely deal with water quality issues. And so again, to answer that question, that we often get asked, what are the benefits of increased snowpack and subsequent stream flow? It's a significantly complex question. So how are we analyzing cloud seeding, right? The validation aspect is something that everybody is sort of interested in. And it's really a three-pronged question for the state of Idaho, and that starts with, what is the amount of increased precipitation from cloud seeding operations, right? How much did we increase that snowpack? In Idaho and across most of the programs in the northwestern US, historically we've utilized a target control or a statistical type analysis. So comparing climatological data from one basin that is very similar to our target basin, developing a relationship, and then measuring the percent change when you start cloud seeding. And that percent change is largely what we've attributed to an increase in precipitation. The challenges with that are those are largely point measurements, right? And so we can only get an average across the basin, and when you're looking at complex mountainous terrain, it doesn't do a very good job at really quantifying. And so, as I mentioned, our next evolution is to hopefully move into physically based modeling supported by observations. That image that you're seeing sort of in the middle is an output of WRF weather mod across one of our basins. And so what you'll notice on the left-hand side of that image is the dispersion of silver iodide being in that zigzag pattern. And then the effects of increased precipitation as were modeled in WRF weather mod. And so you can see that there's different areas of dark and light across that basin, and that really captures or highlights the complexities of these mountainous terrains. And so the impacts or the benefits of cloud seeding across these basins are widely varying, and we're certainly interested to better understand that question. But that's only one step in that question, right? So you increase the precipitation, but really we're interested in the cost efficiency. And so that really comes down for us at least to a water volume. And so, well, you increase the precipitation and snowpack, but what does that equal in a water volume? And I think as many of you would probably acknowledge, that's a bear of a question to answer, because there's different types of snowpacks, which means different water content in snowpack. And then once that snow starts to melt off, there's a number of different physical processes that will occur as that water flows downhill. So evapotranspiration, groundwater saturation. By the time that it actually makes it to a stream gauge, that's not a one-to-one relationship for how much you increase the precipitation relative to the volumetric output in that basin. And so how are we attacking that? Well, models, is largely what we have, and obviously physically based observations is the first and foremost preference, but we do have large observational gaps, and so how do we mitigate for that? And we are working very hard to try and develop our modeling technologies, hopefully a WRF-based model that will be easily coupled with a cloud seeding model so that we can go from that conversion of increased precipitation to a volumetric output. But then going back to the state agencies, and for a lot of us, how does that affect basin hydrology and use? And so first step, you've determined the increase in precipitation, the volumetric output, and now where does that water go? And so that's really where we're at in the state of Idaho, given the complexities and a lot of the advancing research that are currently happening to support the first two steps of that question. And so currently we do have a pretty well-developed water regulation model, and how we are looking at that right now is by essentially just taking some ranges of increased water supply and trying to understand how that affects our system. So regardless of where that water supply came from, for example, if you built a pipeline, if you trucked it in, if you cloud seeding it in, it doesn't matter where the water supply came from. If we add an increase in water volume to our system, how does that impact our system? And that is very significant for our stakeholders to understand, in that while we do have some good evidence from target control and some of our modeling outputs, we can at least look at a range of what increased water supply would affect, how that would affect our system. So moving forward into the research and development, one of the things that I haven't mentioned yet is when the state first began its contributions. The state's initial contribution, when I began with this program in about 2018, our annual program budget was about $700,000. Today, our average annual budget is in the neighborhood of $5 to $7 million, so significant growth. And a lot of that has been in research and development to further understand how cloud seeding impacts our basins and how we can become more efficient. So some of the other research aspects that we're working on are different seeding agents. So liquid propane, for example, we have had some operational projects. There has been some evidence to demonstrate that it can nucleate ice at warmer temperatures. It doesn't rely on orographic winds, so it must be dispersed in cloud, and it is less costly to operate. And so this is not something that we believe would replace our existing infrastructure, but more support as an enhancement tool to our different projects and programs as it can work at different temperature ranges. And given that it doesn't rely on orographic winds, it may open up our opportunities to look at cloud seeding in different regions. And so this liquid propane project was actually one of the first research projects where we began collaborating with other states. And so this is very significant because we sort of get to a point in the state of Idaho where we've made large investments into research that really support the broad community. And I think there's some sentiment in our state that why don't we have support, right? Why aren't there other communities investing in this research? Because they equally have a need to understand some of this. And so for the state of Idaho and the state of Utah, that this partnership is very significant, right? Because it's the first time that two of our states have come together to advance some of this research. And Utah, state of Idaho and the state of Utah being the two largest programs in the United States. So further on to that collaboration, our states have started looking into the use of silver iodide. We've heard from other folks, that there is maybe concerns for using silver iodide as a seeding agent. And in the state of Idaho and a lot of our programs, we largely haven't considered it to be a concern, and that is because of concentration, right? Any material out there, the effects of that material on your environment, on human health, on a number of other different things, is going to depend on the concentration. And so for some numbers, for example, our flares are about 15-gram flares, so a couple ounces, if you will, of silver iodide being released on a seeding mission. And so I often like to describe this to folks. If I gave you a small ramekin or a small cup of a powder and I dumped it out of an airplane over a large basin, what's the likelihood that you'd ever be able to find two particles of that same container in one area? And so that's, again, largely why it's the concentration issue. We don't feel like it could ever accumulate. But that's not to say that as more projects and programs come online and we start growing, that may not be an issue. And so I think we have an ethical obligation to be responsible to the public and to ourselves to answer these questions. And so this year is the first time that all of the different agencies in the United States actually came together to assess the use of AGI for cloud seeding. That has been done through the North American Weather Modification Council, which is essentially a consortium of 28 different states and public agencies who participate in cloud seeding. And so again, this is very significant because we are finally getting these collaborations to move forward some of these research questions, which oftentimes can be limited either by policy or by funding or by a number of different complexities. So last few things I'll wrap up with, some of the other things that we are investing in, modeling improvements, I've talked about quite a bit, but you obviously need data, observations, tools, and technology to improve those models. And so how do we get that data? How do we improve our observational network? That's very costly. And so then we start looking at who else could benefit from this, who else would be interested in these observational networks so that we can all benefit from this data and move forward. And then obviously aerosols we've talked about, largely within our models. The Snowy Research Project, for example, only looked at aircraft primarily. So there's still a number of different things that we recognize that we need to improve in our models and the model physics and understanding aerosols and how they work in our projects and programs. And we're really trying to advance some of that research within our state. So wrapping up, I'm just going to provide some of the key points with regard to program administration, which I feel are really what what create the most complexity. And I've spoken on this, quite a bit already, but program funding, again, our states rely on the availability of public funding, and these states have obligations to manage a number of different responsibilities beyond water, even though water is really, most industries rely on water. Then you add in the complex water management. You have multiple administrative boundaries. So how do you manage water systems across those different boundaries? Again, I've made this comment numerous times, neither water nor weather adhere to those boundaries. And so if you look at the United States, we have a lot of boundaries. And so managing those systems becomes infinitely more complex, and we have become infinitely more reliable on these collaborations to come together and advance. Long-term monitoring and evaluations. These are things, again, as public agencies, we must be responsive of. The quantitative analysis for cost efficiency, but also ensuring that we are not having any environmental or public health and safety considerations. And so to do that, again, we have the long-term availability of data. You need data, tools, technology to really conduct this long-term monitoring and evaluation. And as a state who is just now, kind of getting into cloud seeding, this is a lot to take on and understand. So relying on those collaborations and partnerships becomes very significant. And then obviously the public interfacing and communicating all of this to the public and helping them understand, especially in the face of misinformation today. So my last slide today, I just wanted to wrap up with this key point in our projects and programs, and largely why I feel we've been successful and hopefully in alignment with some of the reasons why we're all here today. And that is largely, again, going back to these three pillars. And so the triangle being the strongest shape in nature, I think, is also going to be the strongest shape to move us forward and advance in this industry. And so we must rely on the research, as we've talked about, but also this collaboration between private industry, who also can make these investments, and how that impacts the government and the human dimension. So answering these questions collectively, how can we collaborate? Are there the health and safety concerns? What are the other opportunities for cloud seeding? How can we utilize cloud seeding in different basins? And what are the implications, long term across a wide scale of different industries? And so these are all things that I'm very honored to be here today and to learn from you all and share these ideas, because it is really the basis of why our projects and programs have been successful to this point. So that is my last slide, and I will wrap up by saying again, thank you for this opportunity to come before you all.
Thank you, Ms. Golden, for your valuable contribution. Next, we have Ali Abushaib, professor at the High Mountain Geophysical Institute of Russian Hydrometeorological Service.
Good afternoon. At the beginning, I would like to express my deep gratitude for the whole organizing committee of United Arab Emirates Enhancement Research Program, and for all people involved into this really fruitful and helpful event, and for constructing this comfortable and fruitful ecosystem and infrastructure, allowing us together to meet and to share our knowledge, our findings, and some visions how to move forward this specific field for the new frontiers. In my today talk, I would like to tell you about our past results obtained in frames of the previous IREF project, share our vision how to improve and how to develop this technology further. And the aim of this project was to stimulate artificial local-scale convection, which may induce formation of artificial cloud in favorable weather conditions. So we all know that about 2.2 billion of Earthlings suffer from shortage of fresh water, which is getting worse as the world population, the climate change, and desertification grow. And this shortage is partly mitigated by technologies such as seawater desalination, extraction of groundwater, extraction of low salinity offshore waters, even harvesting of fog waters and other technologies. However, this problem continues. And rain enhancement is one of the options, and it allows to add from 5 to 25% on the average of additional precipitation in its beds realizations in different regions. However, in desert regions where the natural rate of precipitation is small, like 100 millimeters, additional 7 to 10 millimeters is very low amount, and it does not solve the problem. And limitation of traditional cloud seeding technologies is that when we don't have clouds, even when we have clouds but they are not seedable, we don't have opportunities to increase precipitation. At the same time, we know that atmosphere permanently contain around 13,000 cubic kilometers of water vapor. And it makes around 9 cycles per year. And this amount of water is like 5 to 6 times more than all rivers on Earth. And it's a really good opportunity for us if we find a way how to extract a part of this atmospheric water, a way to replenish the water scarcity. And the question arises here is, can we actually create artificial cloud or increase the power of natural clouds to increase potential for artificial rain formation? And observations, for example, of pyroclouds, industry clouds over large fires, nuclear and thermal power plants, thermal islands over megacities, and warming mountain slopes testify the basic principle of this possibility. And in frames of our previous project, we testified several different concepts, and we focused on some of them while postponed in others. And it is also worth to mention that majority of this atmospheric water is located in a lower 3 to 4 kilometers layer over the surface. And in our project, we considered the concept of jet aerosol technology. It's based on the use of turbojet aircraft engine and special devices to rotate the output jet of the engine upward in order to create the artificial updraft. So the physical basis is that it allows to create artificial ascending, high-speed, high-temperature flow in the near-ground atmosphere. It consists of combustion gases, hygroscopic aerosol, water vapor, and environmental aerosol, and so on. And when this jet is propagated vertically upward, it expands, and it also there is an impact of side wind and so on, and the buoyancy is decreasing with height. And the purpose of adding hygroscopic aerosol, different types of hygroscopic aerosol, is not only to trigger droplets formation, but also to enhance the buoyancy of vertically ascending artificial air. And in favorable weather conditions, such high energy updraft may trigger formation of artificial cloud. And this is the illustration of the field site. It was in United Arab Emirates on the highest Jebel Jais mountain. And here you can see the main carrier buoyancy jet produced by the engine and additional 2 jets produced by fog cannons. And fog cannons allowed us to spray different types of hygroscopic materials into the carrier jet. We sprayed around 9 different types of hygroscopic materials, like water solutions of sodium chloride, carbamide, calcium chloride, and also dry form of these substances. We used a milling system, and also we tested a novel seeding material developed by Linda Zhu team and Khalifa University. And 2 field campaigns conducted in Jebel Jais mountain showed us that this is, yes, it's principally possible to create artificial small volume, short-living and semi-transparent clouds. And sometimes we got very short precipitation, but it's not of practical applicability. It does not solve the problem. And there are several reasons behind that. For example, one of them is that hygroscopic materials which we used, they are not acting as condensation centers as fast as we expected. And therefore, the energetic feeding to the ascending air is not that fast. And also, the dry air, local atmospheric conditions, they prevented the action of this technology. But the first campaign was very, especially dry atmosphere, while second one, we got much more favorable weather conditions. And here you can see some indications of artificial cloud medium observed during experiments. This is the table showing us different types of hygroscopic materials that we used. For example, calcium chloride starts condensation at a very low humidity from 6% of relative humidity, while others starts condensation later. And the purpose of using these different types is to supply, to make energetic feeding on different levels. And different levels below natural cloud base. This was one of the very dry conditions day. And despite of that, 11 minutes later, we saw a lot of condensation trails in a clear sky atmosphere before experiment. And here too, you have different signatures of artificial cloud medium. This is another day. We see quite high vertical propagation of the updraft and condensation trails. Comparing to the nearby summit of mountain summit, we assessed the height more than 1 kilometer in a vertical dimension, in a visible channel and in infrared channel. And this is an illustration how dry atmosphere can be here. The radiometer data showed us extremely dry atmosphere. It was a characteristic of our first field campaign. And it's prevented a lot the efficiency of this technology. I don't know why, but video doesn't work. And we were surprised to know that the updraft formed by the engine is actually a vortex well-developed vortex. And it makes the updraft more stable and resistant to the side wind. And it is very important. And numerical simulation using computational fluid dynamics showed us similar result. So natural field experiment against simulation was very similar. And we deployed the copter drone with sensors, with kit of sensors to measure aerosol droplets content, to measure wind, temperature, and other parameters. And once we entered the updraft medium, here it is on height 350 meters, we detected the jump in 10 micron size particles, 2.5 and 1 micron size particles. It means that there we captured the probably droplets and aerosols exactly inside the updraft. And this is another signature using wind LiDAR. You can see the red spot, red points on the background of blue field. It shows us that the direction of the air motion is different. And blue color shows us environmental air motion, while red points show us air motion inside artificial updraft. And the wind profile was very comfortable for us to work. Up to 2 kilometers, wind was less than 5 meters per second. This is another situation, and again we saw semi-transparent, short-living artificial clouds over the field side. And we also captured differences in action of novel seeding materials against sodium chloride and calcium chloride. And the artificial cloud medium probably was denser with novel material, rather comparing to other types of hygroscopic substances. And also we detected some interesting features, like for example, when there are small natural clouds and the updraft, the artificial updraft is acting, so those small natural clouds started moving toward each other. Like entrainment of the ambient air and existed small clouds, and we observed some swirling and moving toward each other. This was one of the interesting findings. And in some of experimental cases, natural stratus and stratocumulus clouds passed over the site, and we were inside actually natural clouds. And such an intensive hygroscopic seeding, which we realized, I would say, is never reproduced neither by aircraft nor by rocket systems. So as a day before, John represented us the orographic seeding using drone and the clearing of the whole inside cloud. Here we got similar results. In all cases, we saw increased visibility tunnels over the jet engine system. And it means that not only dynamic, but also microphysical impact on existed clouds were very active. And in two of the experiments, when such clouds passed over the site, we detected radar signatures. On the downwind side, like 10 minutes later, after beginning of experiment, we saw green points showing us increase in radar reflectivity by a factor of 14 to 25 dBz. And I got even droplets, raindrops on the screen of my drone control panel in one of the experimental days. And also, we spent a lot of our efforts and time for numerical simulation and validation. And we deployed supercomputer, and the flow was simulated in two stages. First stage was compressible because the flow was supersonic, and the second stage was undersonic, and it was just atmospheric flow simulation. And we utilized computational fluid dynamics model. And for example, for one simulation, the mesh, which was adaptable in areas with high physical parameter gradient, the cell size resolution was the highest, while near the border it was the lowest. And for example, for this case, the mesh consisted of 40 millions cells, numerical cells. And you can imagine such just one event is computed several days on a supercomputer. And this is an illustration from the model again, how the side wind impacts and affects the vertical propagation of the updraft. On the left-hand side, this is just 1 meter per second, and on the right-hand side, it was a real upper air sounding data from Abu Dhabi station. And the difference in vertical propagation is more than 2 times. And our further investigation showed us that we need to enhance the performance and capacity of this technology in order to obtain better results. And one of the possible developments is utilization of faster working, faster acting hygroscopic substances, releasing more latent heat of condensation in order to supply buoyancy to the weakening updraft. And here you can see what can happen if we increase the power of the engine. If we deploy 1 engine, 2 engines, 4, 8, and 16 similar engines at different temperature lapse rates. And comparing, for example, 1 engine and 60 engines, we see the order of magnitude difference in height, in vertical propagation, and voluminous propagation of this artificial cloud. So the vision is to increase the number of such engines, or maybe using much more powerful engine. I will say later about that. So another vision how to improve is to deploy, we compared different hygroscopic aerosol loads to the jet. For example, and in this case, we simulated sodium chloride and nanopowder, and found also when we increase the load, amount of seeding materials introduced into the jet, we enhance the condensation, droplets activation, and it also makes the vertical propagation higher than with a low load of hygroscopic aerosol in the jet. And one of the further development which we are started thinking on is application of aerospace engine. For example, NK-33 engine and others engines, they are 100 times more powerful than turbojet engine, which we used in previous work. And here you can see on the upper level, you can see tests of this engine by Rocket and Space Corporation Energia in a Moscow district. And you can see really high plume released from the pipe. And here I want to say that this is in these experiments, in this test, engineers try to reduce the power of the output jet many times by spraying water into the jet, by adding some expansion chambers and other techniques. And this is just maybe 5 to 10% of the whole energy, and still you have really high plume. In the bottom line, this is illustration of test of the largest hydrogen-fueled engine conducted by NASA, and according to observations, there was a light rain. And these are parameters of this NK33 engine. And the thrust of this engine is like 30 times more than a turbojet engine we used. And this is the first numerical experiment that we conducted for this aerospace engine. Unfortunately, domain was just 1 kilometer, but despite that, it took 9 days to compute this image. And here we can see quite voluminous and deep convection produced by such an engine. And also there are some challenges. For example, in order to introduce hygroscopic substances into the jet, we need to find some technical solutions. We simulated supersonic flow of the jet, and when we simulated releasing of hygroscopic materials in the left side and on the right side of this carrier jet, we saw that actually the entrainment of these hygroscopic substances is not that good. And they continue to be separated from each other, main carrier and additional jets produced by other systems. So this is something which we have to consider and pay more attention. We got 4 patents of invention for this technology, and another one will come soon. So to conclude, what are the main problems and uncertainties at the moment? So we don't know how much can dry atmospheric layers affect the updraft moisture content. And moisture is lifted from the ground level upward, but how does it change the upper layers? Moisture content in the upper level. What should be the updraft lifetime to ensure slow condensation growth of activated droplets to the size of rain drops? Is there enough time for hydrometeors to grow to this size? And are those precipitable particles are actually able to reach the ground level? And we also realized that we need to develop further our numerical facilities, and we need to construct new types of models, like a combination of fluid CFD computational models, WRF model, 3-dimensional cloud resolving model, which will cover all different stages on very different space and time scales. So during implementation of previous project, we obtained a fundamental conclusion that jet aerosol technology can work when atmosphere is favorable for that. But those obtained effects were lower than expected, and the main reason for that is the energy of this device, of this technology we developed, which is probably on the lower threshold of action. And preliminary numerical calculations showed us that an increase in the power of such system by a factor of 16 allows to increase the vertical height by a factor of 3 and the volume by a factor of 10. So further development of the concept may be directed toward strengthening the device by increasing the number of engines or by utilizing much more powerful aerospace engine. And it is necessary to conduct numerous numerical simulations to optimize whole technical implementation of these technical systems, to deploy them in optimal days with favorable weather conditions. So this is a long way, and this is just a beginning. And thank you very much for your attention.
Thank you, Dr. Abshai, for your detailed insights. Our final technical presentation will be delivered by Zanyu Yao, Chief Scientist at the Chinese Meteorological Administration.
Okay, thank you very much. Good afternoon, everyone. Very nice to have an opportunity here to introduce some of the Chinese new weather modification works. My topic is the Chinese acoustic weather modification and its effect evaluation. It was include 4 parts. First, I just want to introduce some of the background of our work. As we know, the traditional weather technology include the aircraft and rocket, artillery, and also ground generation. But it may have some of the potential risks in recent years in our research. So another type of the physical weather modification technology have implemented in China for many years. It includes the acoustic waves technology, the ionization technology, and the femtosecond laser. Mainly, these 3 physical weather modification technology are used nowadays in China for laboratory studies and also for the field experiment. Today, I just want to introduce the acoustic rain enhancement technologies which have been studied in China for the past several years. And the physical weather modification technology can be the complementary technology for us to comparing to the traditional weather modification technologies. Now, I just first want to introduce the acoustic agglomeration and the laboratory experiments in our work. The acoustic agglomeration is that a certain intensity of sound waves exacerbate the relative movement among droplets. The basic interaction phenomenon is the viscous caused drive of the acoustic waves on particles. That is, the sound waves drive the air into oscillatory flow, and the flow acts on the droplets by the viscous binding force and transfer the momentum to droplets. These agglomeration stimulated by the sound waves finally destroy the cloudite stability of the clouds, which makes the precipitation happen. Some of the laboratory experiments and also the numerical calculations on the mechanism of the acoustic precipitation have been done in many places. And the influence factors of the acoustic weather modification technologies usually include, the main factors include the frequency, the sound pressure level, the initial particle size spectrum distribution, and also the sound wave operation time. Also included the environmental conditions such as the temperature, humidity, and pressure, etc. So these several photos showed us that the acoustic laboratory experiment in Tsinghua University of China, and also in some of the institutes for example, in Russia and in Germany. They also do some of the laboratory works focused on the acoustic agglomeration laboratory works. These photos also show the laboratory experiments in China, especially in Tsinghua University. We do some of the laboratory works during the past several years. These photos show us some of the results of the laboratory experiment for fog dispersals. For example, under the natural circumstances, the median profile size of the cloud droplets will increase for about 10 minutes, and then to reach its maximum value, and after that it began to decrease. And usually the frequency of the acoustic waves is under the 100 hertz, especially under 50 hertz. In our experiment, we can find that about 40 or 50 hertz acoustic waves are the best which can be used to eliminate the droplets. And these photos showed us the relationship between the droplets changes virus the different frequency of acoustic waves in our laboratory experiments. And these several photos also shows that when the local frequency is used and a higher sound wave pressure, normally much than 125 dB, have a more sensitive promotion effect to the dispersion of the fogs. let's see one of the videos. We can see that the left is the blank. Let me see. The left is the natural dispersal of the fogs without any intervention. And the right is the intervention by the acoustic at the 130 dB. So we can see the difference appears after 4 minutes. After 4 minutes, the quite significant difference with the two situations we have showed here. Also, many field experiments have been done in China during the past several years. I think since 2015, we have begun to study to have the acoustic rain enhancement field experiment. Since then, we have already implemented about more than 20 field experiments of acoustic rain enhancement in about 10 provinces in China. These figures show the spots of the field experiment in China during the past 6 years. And this slide shows the development of our acoustic equipment. So far, our acoustic equipment have already passed the 4 generations. And the acoustic rain enhancement field experiment, I can show you some of the scenes. For example, the left is in 2018 at Qinghai University, and the right is the next year in Qinghai province. We have done the field experiment. And these is some of the results we have already get and published in the journals, and to show some of the results of our field experiment. Now, I want to introduce one of our field experiment in Linzi of Tibetan in 2020. We can see that we have the 3 zones. The left is the experiment room. The middle is the transition room. And the right is the contrast room. And this is just the situation of the valley of the real seams. And in this field experiment, we have our the criterion, and also do the experiment during the 1 year using the random test based on our random platform. And we selected the acoustic operation for the random test, and also without operation, we called it the monitoring type. So these 2 schemes we have using different comparison, or just to for the comparison to just to find what the result of after the comparing. So using the comparison analysis, we can see for the right hand of the pictures, we can see that the maximum proportion of increased rainfall appeared in the experimental zone. And the proportion of the increased rainfall gradually decreased from west to east. So the down tables just show us in the 3 different rooms, using the comparison analysis, the different results have showed us in this table. And we also use another statistical method, which is the double ratio analysis method, to do the result evaluation. The right top table, we choose the transition zone as the control area, and the right down table, we choose the contrast room as the control area. And the left table just show that we use the transition room and contrast room together as the control area. So under these 3 schemes, we use the double ratio analysis to analyze our data collected in the field experiment. And these 3 tables showed us the final statistical results. And the rain enhancement rate is from about 4% to 14% of the enhance of the ground precipitation. Another field experiment in Leizhou city of Guangdong province, China, in 2023, I also want to introduce some of the results of this field experiment. This is the some of the information of the field of Guangdong province, and also we use the statistical evaluation to use the target area and control area. And the control during the experiment, the cloud movement was mainly influenced by the southwest wind and followed by the southeast wind. So under these 2 situations, we just divided into our data into 2 groups. The group 1 affected by the southwest wind, and the group 2 affected by the southeast wind. So divided into these 2 groups, we used several statistical evaluation to assess our field experiment. This is the group 1 evaluation results. We use also 2 methods. One is the double ratio analysis. The other is the regional regression analysis. And based on the group 1 randomized experiment data, we finally get the result of the about 40% of the increased rain rate, and it's passed the significant test. For the group 2, we also using the same 2 statistical method, which is the double ratio analysis and regional regression analysis. And also, we get the similar increased rain rate of the ground precipitation. And also these results also pass the significance test. For the physical evaluation, I just show you the 2 situations. The case 1 is the situation when it shows that when the operation, we can find a similar development trend of the cloud cells or cloud unit, which have the similar development trend with the operational or target units. So we can find at the same time for this case. So we, under our criterion, the criterion of the selection of the control unit, all of the cases we followed one standard, and this showed us the movement of the cloud unit development. And these five photos showed us the final physical evaluation results. And we choose 5 radar factors, which we can choose any 5 one, but whenever we choose these 5 factors, all the cases are using the same factors. So we chose the radar parameters of the maximum reflectivity factor, the vertical cumulative liquid water content, the precipitation flux, error volume, and error top height. So all of these 5 factors, whenever we select it, all of the caves can be used for the same. So we can see from these pictures that it's shown that after the operations, quite a big difference happened. The blue one is the operation unit, and the red one is the natural cloud development unit. So the quite difference happened after the acoustic rain enhancement operations. Another cases just have the different situation because when the operation, we cannot find a similar cells or unit at the same time. So we can find it before or after the operation to choose one of the cells which have the most similar development trend with the operation unit. So during these cases, we just following our criterion to select the most similar the unit, the cloud unit, as the control unit. So these cases also shows that the difference is for the horizontal axis. It's not the real time, but it is the for these cases the horizontal axis is the lifetime of the cloud unit. So comparing of the blue line and the red line, we can see that quite difference happened after the operation. And also it can be shown that the target unit stimulated by the acoustic operation have postponed its lifetime comparing with the natural development of the cloud unit. And our acoustic rain enhancement technology have been imported to Thailand last year. So from last year, our field experiment also implemented in Thailand. And Thailand participation institutions include the Agriculture Research Development Agency and the Department of the Royal Rainmaking and Agricultural Aviation, and also the Thailand's Agricultural University and the Royal Irrigation Development Department. So in Thailand, our purpose of the field experiment of acoustic rain enhancement focused on the reservoir impoundment and the agricultural irrigation and water replenishment. So far, we have installed our rain gauge and also some other equipment to in Thailand at the two spots. One spot showed us here, and the other spots, and both these two spots have the replenishment of the water of near dam. And also in China, we have some other acoustic rain enhancement of the field experiment. For example, from this year in Souxian County of Anhui Province, we will do the acoustic rain enhancement field experiment focused on the effect evaluation. And in the Yunnan Shanxi province of China, our purpose of the acoustic rain enhancement field experiment focused on the underground water replenishment. And also in Yunnan province, our purpose of the acoustic rain enhancement focused on the Dianci Lake water quality control. So in some of the other provinces, during these several years, we have already implemented several acoustic rain enhancement, and we hope we can get some more results on this abstract. And also, another work for the acoustic weather modification focused on the fog disposal. We also do the fog disposal field experiment based on the acoustic waves. Now, we have done some of the work in Beijing, Henan, Jiangsu, Zhejiang, Guangdong, some of the provinces in China from this year. So finally, I just gave the short summary. The numerical laboratory test and numerical simulation study have shown that low-frequency, strong acoustic waves can promote the aggregation and collision of the cloud droplets or aerosol particles, which can trigger warm cloud precipitation mechanism. The field experiment and their effectiveness test in multiple locations have shown that low-frequency, strong acoustic waves can effectively alter the macro and microstructures of the characteristic of the cloud system and increase the surface precipitation or disperse the fogs in the affected areas. And the technology of using acoustic waves to affect cloud precipitation and fogs as a physical intervention technology has the advantage of no chemical pollution, no aircraft restriction, and low operation costs. So it can be used as the supplement to the traditional weather modification and cloud seeding catalyst technologies. Thank you very much.
Distinguished guests, as we are way over time, we're way over time, so we're gonna close the IREF and we're not gonna do the last panel discussion. So as we conclude the 7th International Rain Enhancement Forum, I would like to take a moment to thank all experts, panelists, and participations for their insights and contributions over the past 3 days. This forum has truly served as an invaluable platform for fostering meaningful collaborations, exchanging innovative ideas, and addressing key topics that are crucial to advancing the field of rain enhancement. We are excited to continue this journey, encouraging all of you and your global network to apply to our 6th cycle call for the proposals, and look forward to welcoming you all next edition of IREF. Thank you and have a great day. Guests, if you can just join us on the stage for a group picture.